How does the sun's hidden core create the steady light we see each day? What delicate balance keeps the sun from collapsing or exploding? Why do sunspots and solar flares erupt on a star that otherwise seems so calm? In the silent expanse of space, a gentle light spills across the void. Every dawn on Earth, as night yields to day, this light returns, painting the sky in soft gold and rose. It is our sun, a star in its prime, steady and life-giving. For countless mornings it has risen, and for countless more it will continue to rise, a faithful guardian of daylight and warmth. Each day, the sun's warmth touches the surface of our planet. It bathes fields and forests in gentle heat. Under its tender glow, green leaves unfurl and turn toward the sky, drinking in the light to weave the energy of life. With the first light of morning, birds stir in the trees and flowers slowly open their petals, drawn by the gentle call of daylight. The seas sparkle with morning sunlight, and the cool air of night slowly gives way to a comfortable warmth. We live and grow in this daily gift, often without a second thought, as the sun quietly tends to our world. To us, the sun feels eternal. Ancient peoples greeted the same bright disk rising in the east and watched it set in the west. They built sundials and temples to mark its path, honoring a cycle unbroken through generations. In a world of change, the sun's presence is a comforting constant, a golden anchor in the sky. Even today, we trust that each new dawn will come, the dark of night always gently overruled by the sun's returning light. For now, it stands in the full bloom of its life, a star gracefully middle-aged. Born over 4.5 billion years ago, it has burned for eons, yet remains steady and strong, not yet nearing its decline. In the vast timeline of stars, ours is comfortably settled into its long midlife, shining with a reliable glow that nurtures everything we know. For all its uniqueness to us, the sun is but one star among countless stars scattered through the galaxy. Yet to Earth, it is singular, the source of light and life, a gentle fire that shapes our days and seasons. Each ray of sunlight carries the silent story of the star that created it, reaching across 150 million kilometers to warm a child's face or spark a seedling's growth. In its prime, the sun gives and sustains, quietly weaving the conditions for life to flourish on our tiny world. From our earthly vantage, the sun is a bright circle we can hide behind a raised hand. Yet in truth, it is immense beyond our imagining. Over 1 million Earths could fit inside it, and its mass far outweighs everything else in the solar system combined. The sun is a colossal sphere of hot, glowing gas, and we live in its outer reaches, bathed in its light. But at just the right distance, it nurtures rather than harms, a gentle giant sustaining its tiny companions. For now, the sun seems unchanging, a comforting beacon. But deep inside that shining sphere, something extraordinary is happening. There, hidden from our eyes, a great and constant fire burns, fueling the light and warmth that reach us here. It is a secret of the sun, a secret of creation itself, quietly powering our days. Deep in the sun's core lies the secret of its steady shine, a continuous fire of creation. Here, the environment is unlike anywhere else we know. The pressure is unimaginably high, the temperature extreme, well over 10 million degrees. In these conditions, the simplest element in the universe, hydrogen, is transformed. Atoms that would normally never meet are pressed so close that they fuse together, merging into a new element, helium. Inside this hidden furnace, atomic particles are pressed into an intense, never-ending dance. If several hydrogen atoms manage to join together, they become one helium atom, and in that instant, a burst of energy is released. This is the sun's secret, a delicate alchemy of matter becoming light, happening on a colossal scale behind the sun's shining face. As hydrogen atoms fuse, they release energy that floods the core. It is not a fire of flames, as we know on Earth, but a fire of pure atomic creation. Each union of atoms emits a tiny spark of light and heat. These countless tiny sparks combine into an enormous outpouring of energy. Every second, deep inside, the sun quietly converts a little of its mass into light. In effect, the sun gives up a part of itself to keep shining, offering millions of tons of its own substance each moment to bathe the solar system in warmth. For the sun, this process has been ongoing for billions of years. It began when the sun was young and first ignited its nuclear heart. Since then, that heart has burned steadily, consuming the sun's hydrogen fuel with measured grace. There is so much hydrogen in the core that this stellar furnace can burn at a nearly constant rate for eons, providing a steady output of light that barely flickers over millennia. Over those ages, helium, the ash of this great fusion fire, has been accumulating quietly in the sun's center. Yet the sun still has plenty of fuel left to burn. It is only about halfway through the hydrogen it was born with. In this prime of its life, the nuclear furnace remains robust and balanced, ensuring the sun's brilliance does not waver. All of this is hidden beneath the sun's glowing surface. No direct glimpse of the core's fury reaches us. The energy must journey outward through layers of dense plasma, gradually making its way to the surface. By the time it escapes the sun, it has been transformed and gentled, emerging as the sunlight that pours down on Earth. In this way, the sun's inner fire runs smoothly, neither too fast nor too slow. It is as though the sun knows how to sustain itself, never letting its vital flame falter. This steady burn is no accident, but a result of a natural balance within the star. There is a harmony between the furious energy pushing outward from the core and the immense gravity pulling inward. This balance of forces holds the sun steady, allowing life on Earth to flourish under its consistent light. For all the raging energy at the sun's core, an opposite force is always at work. Gravity, the same force that keeps our feet on the ground, pulls every bit of the sun's mass inward toward its center. The sun is extraordinarily massive, and its gravity is correspondingly immense. Left unchecked, this gravity would make the sun collapse in on itself, drawing all of its gas tighter and tighter in a catastrophic implosion. But that collapse does not happen, because a powerful outward push resists it. The core's intense heat creates tremendous pressure. The hot gas deep inside wants to expand, and the flood of energy from nuclear fusion radiates outward with force. Together, this internal pressure and outward flow of radiation counteract gravity's inward tug. Like an enormous tug of war in perfect balance, the inward pull and the outward push hold each other at bay. These two opposing forces are evenly matched. The result is a peaceful equilibrium that keeps the sun's size and energy output remarkably steady. The sun neither implodes under its own weight nor blows itself apart. Instead, it rests in a state of balance, as it has for many millions of years. This steady state allows the sun to shine reliably, a constant beacon rather than a flickering torch. If slight changes occur, the sun naturally corrects them. Imagine the core burning a bit brighter for a time, producing more energy. The increased pressure makes the sun's outer layers expand just slightly. As they expand, the core cools and the fusion slows, reducing the outward pressure and letting gravity gently pull the star back inward. Conversely, if the core output drops and the star starts to contract, the core heats up under the added pressure, causing fusion to pick up again. In this way, the sun self-regulates, always finding its way back to a comfortable equilibrium. This automatic balancing act serves as the sun's cosmic safety valve, ensuring that its brilliance stays steady on human timescales. For life on Earth, this steadiness is a blessing. Year after year, century after century, the sun provides a consistent warmth and light. Our climate and ecosystems depend on this constancy. If the sun's energy fluctuated wildly, it would be difficult for life to survive the unpredictable swings. Still, even with this internal harmony, the sun is not entirely calm or uniform. Its surface and atmosphere seethe with activity. Dark patches known as sunspots sometimes freckle its bright face, and sudden flares and eruptions flash from its surface, sending bursts of energy into space. The sun, for all its steady shining, has its own kind of weather and cycles. These dynamic features are another aspect of our star's nature, the many faces it shows as it continues to shine. Seen from afar, the sun's shining face looks smooth and unchanging. But when we look more closely, we discover it has its own kind of weather and seasons. At times, dark blemishes drift across the bright disk. These are sunspots, cooler regions on the sun's surface, formed by knots of magnetic force. A sunspot may last for days or weeks, and as the sun slowly turns on its axis, about once every month, the spots glide from east to west across its face and then disappear, only for new ones to emerge elsewhere. Around these sunspots, the sun can become restless. Sudden eruptions of light and radiation, known as solar flares, flash out from the surface. In minutes, a flare releases an enormous burst of energy, heating the surrounding gas and sending streams of charged particles racing into space. These flares are like stellar storms, brief, intense outbursts that can brighten a portion of the sun and then fade away. The sun also sometimes unfurls giant loops of glowing plasma, called prominences. These immense arches of gas, often tens of thousands of kilometers long, hover above the sun's surface for days, guided by magnetic fields. Occasionally, a loop will break and erupt outward. In such moments, the sun expels a great cloud of particles in what is called a coronal mass ejection, a billowing gust of solar material that surges through the solar system. These events are part of the sun's more violent moods, hurling pieces of itself far into space. Beneath it all is a slow rhythm. The sun's activity rises and falls in a cycle roughly 11 years long. During the active phase of this cycle, many sunspots freckle the sun's face, and flares occur frequently. In the quieter phase, sunspots may almost vanish for a time, and the sun's surface looks more tranquil. It's as if the sun takes a long, slow breath in and out. This 11-year heartbeat is driven by the sun's magnetic field flipping and reordering itself deep inside, a natural rhythm that has been repeating for millennia. Even when the sun's surface is calm, another of its faces can be seen only in special moments. During a total solar eclipse, when the moon hides the sun's bright disk, a ghostly white halo appears around the sun. This is the corona, the sun's tenuous outer atmosphere, extending millions of kilometers into space. The corona shimmers like a pale crown. It is normally invisible against the bright sky, but during the eclipse's darkness, it shines with an eerie beauty. This delicate aura is extraordinarily hot and dynamic, a reminder that even the sun's faintest reaches are alive with energy. All these features, the spots, the flares, the looping prominences, and the ethereal corona, are different faces of our star. They show that the sun is not a static ball of light, but a complex, living system with cycles and outbursts. Yet, despite these wild moments, the sun's overall glow remains steady from our vantage point. We can admire the beauty of an aurora sparked by a solar storm, or marvel at an eclipse revealing the corona, all while trusting that the sun will continue its calm, life-giving shine. And as the sun continually sheds energy and particles, it creates an invisible influence stretching far beyond its visible disk, reaching out across the solar system. From the sun's upper atmosphere flows a constant, gentle stream of particles, the solar wind. The corona is so hot that its particles move fast enough to escape the sun's gravity, streaming outwards in all directions. This solar wind is an invisible breeze of charged particles, mostly electrons and protons, that blows endlessly through space. Though we cannot see or feel it directly, it is always there, flowing past planets and out beyond the farthest reaches of the solar system. As it rushes past Earth, the solar wind encounters our planet's magnetic field, which envelops the Earth like a protective cocoon. The magnetic field mostly deflects the charged particles, guiding them around the Earth. But some of the solar wind's particles can leak in along the field lines near the poles. There, they collide with atoms high in our atmosphere, causing the air to glow. This creates the auroras, the northern and southern lights, those shimmering curtains of green, pink, and violet that sometimes dance in polar skies. These beautiful lights are a direct, visible fingerprint of the sun's wind brushing against our world. The solar wind doesn't stop at Earth. It continues to race outward, past Mars and the asteroid belt, past Jupiter and the outer planets, carrying with it the sun's magnetic influence. In effect, the sun blows a giant bubble in space around itself, a region dominated by the sun's own particles and magnetic field, known as the heliosphere. Within this vast bubble, which extends billions of kilometers outward, the environment is shaped by the sun. Even far beyond Pluto's orbit, the solar wind still drifts outward, though ever more thinly. Only at a great distance, roughly where the Voyager spacecraft are now, does the sun's influence wane, as its wind finally merges into the broader sea of particles in the galaxy. Within the heliosphere, every world feels the sun's touch. When a comet swings in toward the inner solar system, it grows a long, glowing tail. That tail always points away from the sun, blown by the solar wind and by the pressure of sunlight. The atmospheres of planets, especially smaller ones like Mars and Mercury, have been altered over time by this steady particle breeze, which can gradually strip away lighter gases. In subtle ways, the solar wind shapes the surfaces and skies of worlds we might think are far beyond the sun's direct reach. Despite its poetic name, the solar wind is nothing like a breeze we feel on our skin. It is far more tenuous and diffuse. Near Earth, This wind contains only a few particles in each cubic centimetre of space. It is a very sparse wind, one that you wouldn't notice if you floated in it. Yet, because these particles move extremely fast, hundreds of kilometres per second, collectively they have significant effects. During periods when the sun erupts with flares or ejections, the solar wind becomes gusty and strong, and these space storms can shake Earth's magnetic field. We might not feel such disturbances in our daily lives, but our satellites, radio signals, and power grids can register the sun's tempest from 150 million kilometers away. Most of the time, however, the solar wind blows quietly and steadily, a constant background presence in the cosmic weather. It is the sun's subtle breath, unseen yet far-reaching. Through this gentle wind, the sun extends its influence to the very edges of its domain. We live within the atmosphere of our star. Our entire solar system resides inside the sun's expansive, invisible embrace. Space is not truly empty, but is filled with the faint whisper of the sun, reminding us that even across the void, we are connected to our star. In every blade of grass and every leaf, the sun's influence is at work. Plants capture sunlight and use its energy to grow, in a miraculous process called photosynthesis. Using the sun's light, green leaves turn water and air into sugars and also release oxygen. These sugars become food that sustains nearly all life on Earth. Every fruit that ripens, every tree that rises from the soil, is built with sunlight as a key ingredient. Even the energy in the food we eat can be traced back to a moment of sunlight falling on a leaf. In this way, the sun feeds the living world. The sun's warmth also cradles our planet. Earth orbits at just the right distance from the sun, far enough not to be scorched, yet close enough to receive nurturing heat. This gentle warmth keeps our oceans liquid and our climate mild. Without the sun's steady heat, Earth would be a frozen, barren sphere. Instead, it is a vibrant blue-green oasis, full of life. Sunlight drives the water cycle. It lifts water from the oceans as vapor, forms clouds, and returns the water as rain and snow to nourish the lands. The patterns of winds and weather are powered by the sun as well, distributing heat and moisture around the globe. In short, the sun's energy maintains the conditions in which life can thrive, from coral reefs to green forests to the polar seas. All living creatures, from tiny insects to towering trees, are guided by the sun's cycles. The dawn's first light beckons birds to sing and flowers to open. Dusk's fading glow signals creatures of the day to find rest, and those of the night to stir. Many plants follow the sun's path across the sky, turning their faces slowly from east to west to soak up every drop of light. Over the year, the changing angle and strength of sunlight triggers migrations in animals and transformations in plants. Leaves change color and fall as winter's light wanes, and seeds sprout with the strengthening sunshine of spring. Life on Earth has evolved to anticipate and rely on the regular rhythms of light and darkness. Even within our bodies, there are clocks set to the sun. Humans, like most living beings, have internal rhythms that align with the day-night cycle. We wake with the morning light and grow sleepy after sunset. Our minds and hormones guided by the presence or absence of sunlight. Sunlight also helps regulate our mood and health. A bright, clear day can fill us with energy and optimism, while a string of dark, cloudy days might leave us feeling low. In this way, we remain deeply tied to the sun's daily journey, both physically and emotionally. For humanity throughout history, the sun has been a source of wonder and reverence. Ancient civilizations worshipped it as a powerful deity, recognizing its essential role in their survival. They built monuments, and even massive monuments, to observe and honor the solstices and equinoxes. At Stonehenge, for instance, the midsummer sun rises in a monumental frame, and countless other ancient sites align with the sun's seasonal turning points, serving as giant calendars in stone. Many cultures held festivals on these days, celebrating the sun's role in the cycle of growth, harvest, and rest. A year, essentially, is one grand loop around our star, and each season is a chapter influenced by how sunlight falls on Earth. Since the dawn of humanity, the sun's journey across the sky has been our fundamental clock. The rising sun brings morning, its height at noon marks midday, and its setting brings evening and night. One rotation of the Earth relative to the sun defines our day, and this simple cycle of light and darkness has always structured human life. Long before mechanical clocks, people tracked time by the sun's position. A lengthening shadow on a sundial told the hour in ancient town squares. Farmers would work from sunrise to sunset. Even today, in our age of precise clocks, a golden sunrise or a brilliant sunset can feel like the truest indication of time passing. The phrases we use, sunrise, high noon, nightfall, all speak to how deeply the sun's daily rhythm is woven into our language and life. Beyond the day, the sun also defines the larger cycle of the year. It takes roughly 365 days for Earth to travel once around the sun, and this journey, combined with the tilt of Earth's axis, creates the seasons. As the months pass, the sun's path across the sky changes, climbing higher in summer, sinking lower in winter. Days lengthen and shorten accordingly. These changes in sunlight mark the turning of the seasons, spring's rejuvenating light and autumn's fading glow. Since ancient times, people have marked these seasonal solar changes. They built calendars and even massive monuments to predict and honor the solstices and equinoxes. In places like Stonehenge or ancient temples, the rising sun on these special days would line up perfectly with stones or pillars, heralding the change of the season. Many cultures held festivals on these solar milestones, celebrating the sun's role in the cycle of planting and harvest, of cold and warmth. A year, essentially, is one grand loop around our star, and each season is a chapter influenced by how sunlight falls on Earth. Even extremes of time and light are defined by the sun. Near Earth's poles, the usual pattern of day and night stretches to its limits. In summer, the sun may never fully set for weeks, leading to the surreal midnight sun. In winter, it may barely rise above the horizon, plunging those regions into prolonged twilight or darkness. These polar days and nights show how fundamentally the presence of the sun defines what we experience as time. For most of us, though, the sun's regular rise and set is a dependable metronome. We still organize our schedules around it. School and work begin in the daylight hours and end before night. We count our days, months, and years by the sun's cycles, whether we consciously think about it or not. Every clock on our walls ultimately traces back to the cosmic dance between Earth and sun. When we celebrate a birthday, we are really celebrating another full orbit our planet has made around the sun. The sun is thus not only the source of life's energy, but also the celestial timekeeper of our lives, guiding the rhythms by which we grow older and the world around us changes. To us living in the sun's light, our star appears steady and unchanging beyond the daily rising and setting. But the sun, like all stars, is slowly evolving. Over very long spans of time, changes unfold that are too slight for any human to notice in a lifetime. Yet they are there. The sun today is not exactly the same as the sun of ages past, and it will not remain as it is now forever. By all appearances, our sun is unwavering. Yet, nothing in the universe stays the same forever, not even our steadfast star. Changes are happening, but on timescales so vast that we do not notice them in our lifetime. Over millions and billions of years, the sun is quietly evolving. In fact, since the sun's birth about 4.6 billion years ago, it has grown roughly 30% brighter. Each eon that passes, the sun inches up in luminosity. This brightening is very gradual, about a few percent every 100 million years. But in the far future, it will have profound effects. If we could fast forward in time, we would see the difference. 1 billion years from now, the sun is expected to shine perhaps 10% more intensely than it does today. That slight increase in energy would be enough to transform Earth's climate dramatically. Oceans would evaporate more rapidly, and the planet could become much hotter, potentially too harsh for life as we know it. It is a sobering reminder that even a gentle rise in the sun's output, given time, can alter the fate of worlds. Yet even this change is just a prelude to far greater shifts in the sun's life to come. For now, the sun remains in a long, stable phase, burning hydrogen steadily in its core. But deep inside, the balance we've discussed is slowly tilting. Hydrogen fuel is being steadily consumed and turned into helium ash. One day, in the very distant future, the core will run short of hydrogen. When that day comes, the sun's peaceful middle age will draw to an end. The delicate equilibrium between pressure and gravity will falter. The sun, striving to regain balance, will begin to change in fundamental ways that are difficult to imagine from our current vantage point. In that far-off era, the sun will no longer resemble the calm yellow star we know. As the core fuel is exhausted, the sun's outer layers will respond dramatically. Our star will swell and transform, becoming far larger and cooler in color, a red giant. In those days, the sun's gentle glow will turn into a fierce blaze. It will engulf the inner solar system in its expanded embrace, altering or even consuming the worlds that once circled peacefully at safe distances. The sky on Earth, if Earth still exists then, would be filled by the sun's enormous form, its light a deep red hue, its heat overwhelming. Such drastic changes are almost beyond comprehension, separated from us by billions of years. For humanity and all life currently on Earth, these events are practically eternity away. The sun's transformation into a red giant and beyond is the grand finale of its life story, and it will unfold on a stage we will not witness firsthand. But understanding that this change is coming allows us to appreciate the present sun even more, this golden age in which our star is benevolent and stable. Right now, we live in the sun's prime, a calm before the cosmic storm of its old age. It is, in a sense, the sun's afternoon, warm and bright, giving no hint to casual observers of the night that will eventually come. The subtle signs of its aging, the slow increase in brightness, the accumulating helium in its core, are whispers of what lies ahead. In time, the sun will move into a new chapter, and the serene days we have known will give way to a more tumultuous epoch for our star. Yet, in the context of a human life, or even the span of human civilization, the sun will continue to appear constant and reliable. The changes to come are so distant that for us, the sun's light can be enjoyed without worry, as our ancestors enjoyed it before us. Knowing that the sun is slowly evolving reminds us that all things in the cosmos, even the very source of our daylight, have a life cycle. And so, as we stand here in the gentle sunshine of today, we are witnessing the calm before an eventual cosmic transformation, a peaceful interlude in a much larger story that is still unfolding. For now, the sun shines on, golden and steady, and life on Earth goes on beneath its light. But the knowledge of the sun's future casts its present in a new, poignant glow. Like a long summer day that we know will eventually fade into evening, our star's steady phase will someday transition into something very different. The story of the sun is far from over, and as it moves toward its final acts, we find ourselves at the threshold of those changes, gazing ahead with wonder and humility at what the future holds for our beloved star. Eons slip by, and the sun continues its quiet burn, until, at last, the fuel at its core dwindles. After roughly 10 billion years of shining, the sun will have fused most of the hydrogen in its center into helium. In that distant future moment, the steady fire in the sun's core begins to falter. With less fuel to burn, the core's energy output drops. The pressure that once held up the sun's weight starts to fall off, and gravity, ever present, seizes the advantage. Slowly, inexorably, the sun's core begins to contract under its own immense weight. As the core contracts, it grows hotter and denser once again, squeezing the helium ash that has accumulated there. This contraction acts like a last effort to keep the fire alive, and in a way, it succeeds, but not in the core itself. The intense heat from the shrinking core ignites a shell of hydrogen just outside the core. Fusion resumes ferociously in this surrounding layer of gas that still contains hydrogen. In this shell, hydrogen now burns faster than it ever did in the core, dumping a flood of energy into the sun's outer layers. The sudden increase of energy from this hydrogen-burning shell pushes against the sun's outer layers with new force. Those outer layers, previously held in balance, begin to expand outward. The sun's radius swells. As it expands, its surface cools down and the color of its light reddens. Our once golden sun is on its way to becoming a red giant. This transformation doesn't happen overnight. It unfolds over millions of years. But in cosmic terms, it's a rapid change. The sun grows larger and larger, its glow changing from the familiar yellow hue to a deeper orange, and then to a dark red. During this transition, the solar system would witness a star in upheaval. The sun's formerly steady brilliance becomes more intense overall, even as its surface cools and dims in color. To any distant observer, the sun would appear to bloat and redden dramatically. The equilibrium that lasted so long has broken. Gravity has compressed the core, and the resulting heat has blown the star's envelope outward. This is the beginning of the end of the sun as we know it, the first steps out of a stable adulthood and into a volatile old age. At this point, the sun has left the main sequence, that long phase of stability, and entered a new state. It's now a subgiant growing into a true giant. The changes that were once imperceptibly slow have accelerated. Each passing millennium brings a bigger sun. Its diameter multiplies many times over. Eventually, the sun swells to tens, then hundreds of times its original size, now clearly a red giant star dominating its corner of space. In time, the sun's bloated surface reaches the orbit where Mercury once circled. The tiny innermost planet is completely engulfed and vaporized in the sun's growing embrace. And still the sun expands, its swollen edge pressing outward, day by day, closer to the orbital path of Venus. The sun's transformation into a red giant reaches a terrifying grandeur. Mercury, the innermost planet, has already vanished, consumed in the sun's expanding fires. Soon after, the planet Venus meets the same fate. The sun's swollen red sphere fills the sky where Venus once orbited, its searing heat melting the planet's surface and then engulfing it entirely. What were once distant worlds in the solar sky are now subsumed in the body of their star. As the sun continues to expand, it pushes toward Earth's orbit. In this far future, Earth's situation becomes dire long before actual engulfment. With the sun growing ever larger and hotter, the oceans on Earth evaporate away. Blue seas turn to dry basins. Their water becomes vapor that is eventually driven off into space. The very air we breathe would escape, stripped away by the intense heat and the bombardment of solar particles. Our familiar planet transforms into a barren, scorched rock. Whether Earth is ultimately swallowed whole by the sun, or just baked to a dead cinder, is uncertain. But in either case, it ceases to be the life-filled world it once was. By the time the sun's red giant photosphere reaches what was Earth's orbit, nothing living remains, only a charred, lifeless sphere, if it remains at all. Further out, Mars is bathed in an unfamiliar warmth. The red planet, which has long been a cold desert, finds itself much closer to the bloated sun. Any ice in its soil or polar caps would thaw, possibly creating brief rivers or lakes in the last days before the heat becomes too extreme. But Mars, with its thin atmosphere, cannot hold on to this moisture for long. It too is left desolate, perhaps a bit warmer, but still inhospitable. Mars, however, likely survives the sun's expansion, orbiting beyond the star's direct reach. To an observer on Jupiter, or on one of its moons, the sun would hang in the sky as a vast ruby-red orb, far larger than ever before. Daytime on those distant worlds would resemble a perpetual sunset. The formerly dim sun would now bathe their icy landscapes in a moody crimson light, casting long, dusky shadows. The increased heat might cause the icy moons of these giants to awaken. Imagine the frozen surface of Europa or Enceladus softening at the edges, their subsurface oceans stirring. Saturn's moon Titan, with its frigid methane seas, could warm enough for strange rain showers to fall as its lakes evaporate under the dim red sun. Even Pluto, far away, might notice a slight increase in warmth. These effects would be fleeting, however, brief, warm intervals in worlds still hostile to life. As the sun loses mass through powerful stellar winds and the casting off of layers, the orbits of the surviving planets drift outward. The balance of the solar system shifts. Some outer moons and comets might even be ejected or wander under the changing gravity. It is a solar system in turmoil, inner worlds destroyed or altered beyond recognition, outer worlds experiencing a fleeting summer after an eternal winter. Amidst this dramatic upheaval in the sun's family of planets, the sun's core is undergoing its own profound change. The core is now a dense ball of helium ash left from the hydrogen-burning years. Gravity has compressed it fiercely once hydrogen fusion ceased in the core. In this hot, crushed helium core, the temperature continues to climb. Quietly and inevitably, it approaches a critical point. The sun is about to ignite a new kind of fire, helium fusion. Soon, in a sudden flash, the sun will find a second wind by burning helium, and this will usher in another chapter of its life, if only a shorter one. In the core of the distended sun, the crushing weight and soaring temperature finally reach the threshold for that new kind of fire. In a sudden, intense burst known as the helium flash, the helium atoms in the core begin to fuse into heavier elements, carbon and oxygen. This flash releases an enormous amount of energy in a matter of moments, but instead of blasting the sun apart, it causes the core to expand and stabilize. After this dramatic ignition, the sun finds a brief reprieve, a new energy source that brings a measure of stability back to the star's heart. With helium fusion now burning steadily in the core, the sun's furious expansion halts. In fact, the sun contracts somewhat from its maximum red giant size. As the core expands and cools slightly in response to the helium ignition, the sun's outer layers respond by shrinking and heating up a bit. The colossal star that was a deep red giant becomes smaller, and its hue shifts back toward orange or yellow for a time. The sun is still far larger than it was in its youth, but it is less bloated than at its red giant peak. Under this new arrangement, the sun enters a calmer period once more, a second wind in its long life. During this phase, the sun burns helium in its core much as it once burned hydrogen, though the helium fuel will last for a far shorter time. Perhaps for only a few tens of millions of years, a mere blink compared to the sun's billions of years on the main sequence. The star will shine in a relatively steady state again. From the outside, the star's appearance might seem more stable compared to the wild red giant phase that preceded it. It's as though the sun has momentarily regained some of its old composure, its output somewhat less extreme. The former red giant has transformed into a golden giant, still huge and luminous, but not as fiercely swollen as before. For the surviving outer planets, this phase offers a brief reprieve from the sun's earlier intensity. The sun's overall energy output is a bit lower than it was at red giant maximum, so the extra warmth in the outer solar system diminishes. The raging solar winds calm somewhat as well. However, the inner solar system has already been irreversibly altered. No revival comes to the scorched worlds closer in. The star's temporary tranquility is that of an elder catching its breath, not a true return to youth. However, this peaceful interlude is only temporary. Helium, too, is a finite fuel, and it is being consumed rapidly in the core. With each passing year of this phase, the core quietly accumulates carbon and oxygen, the ashes of the helium fire, since the sun's core will never grow hot enough to fuse these heavier elements. Once the helium supply nears exhaustion, the fusion in the core will begin to wane. The core will again start to contract, and the old balance will tip once more. The sun, having enjoyed this brief autumn of its life, will once again begin to swell and cool as the outer layers respond to the faltering core. The final act of the sun's life is about to commence, as the star prepares to shed its outer self and reveal its final, tiny ember of a heart. When the sun's core exhausts its helium fuel, it faces a final collapse. With no further nuclear reactions to support it, the core, now composed mostly of carbon and oxygen, begins to contract once more under gravity's relentless pull. The shell of hydrogen and helium around the core flares up in response, burning furiously in layers. This drives the sun's outer regions outward again. The sun swells back up into a red giant, this time even more extreme in its dimensions and behavior. The star has entered its last phase of life, a time of instability and flickering brightness. Now, in its advanced old age, the sun becomes highly variable. It expands and contracts in great pulses. One year, it might brighten and grow larger. Decades later, it might shrink slightly and dim, only to surge again. These are the dying throes of a star. Each pulsation is driven by complex changes in those remaining shell-burning layers. At its largest, the sun might reach out nearly to the orbit of Mars, a giant red sphere that grows and shrinks in a slow, rhythmic cadence, like the laboured breathing of a tired giant. With each expansion, some of the sun's material is lifted away from the star. With each contraction, the star settles a bit, only to prepare for the next outburst. During these pulsations, the sun's outer layers become increasingly unbound. The star is losing mass at a staggering rate. What was once a gentle solar wind becomes a powerful gale of stellar material blowing off the sun's outer atmosphere. With each oscillation, more gas drifts off into space. The sun, which spent eons holding itself together, now finds its outer parts slipping away, cast into the void. The space around the sun fills with these cast-off layers, concentric shells and waves of gas containing the elements forged in the sun's lifetime: hydrogen, helium, and traces of heavier elements like carbon. This mass loss accelerates toward the very end. The sun can no longer hold on to its bloated outer envelope. In a series of final breaths, it expels most of its remaining mass. The once mighty red giant is effectively shedding its skin. The core, small, exposed, and intensely hot, is all that remains of the sun itself, and it now shines fiercely, no longer insulated by the layers it once had. Surrounding that exposed core, the drifting shells of the sun's former self continue to move outward, expanding into a larger cloud. The dying star has enveloped itself in a growing shroud of gas and dust, the early stages of what will become a beautiful planetary nebula. At this moment, the sun's core is a white-hot ember, and around it lies a faint, ghostly shell of gas that was once the sun's flesh. The transition is nearly complete. The star proper has contracted to a tiny fraction of its original size, and all its outer material has been thrown off. The stage is set for the sun's grand final display, a last ephemeral bloom of light as the surrounding cloud of gas gets lit from within. The remnants of the sun are about to unveil a sight of ethereal beauty in the darkness of space, before fading away into the cosmic night. With the sun's core now exposed and blazing intensely, the diffuse shells of gas it cast off begin to shine. High-energy light from the hot core streams into the surrounding cloud, making it fluoresce in soft hues of red, green, and blue. What was once invisible gas now becomes a luminous nebula, a glowing bubble of stellar remnants expanding into space. If an observer were far away, they would see a delicate shell of light where our sun once shone, a final, radiant bloom marking the star's passing. This phenomenon is called a planetary nebula, a misnomer from early astronomers who thought the nebulous shapes looked like planetary disks. The sun's planetary nebula would likely form a beautiful sight, perhaps a ring-like structure, or multiple shells of colour, like the iris of a cosmic eye. Gases in the nebula glow in different colors depending on their elements. Hydrogen might glow reddish-pink, oxygen a greenish hue. The nebula could appear as an expanding halo, gradually growing larger and fainter over thousands of years. It is the sun's farewell painting, a last display of beauty created from the shedding of its outer layers. Astronomers observing the cosmos have found many such glowing nebulae around other dying stars. Each one is a delicate, ethereal structure in space, a preview of the kind of elegant farewell our sun now offers in its final moments. At the center of this luminous cloud, the small core of the sun remains visible as a brilliant point of light. This core, now a blazing hot white dwarf, pumps out ultraviolet radiation that keeps the nebula shining. For a brief period, brief in cosmic terms, perhaps only tens of thousands of years, the nebula maintains its bright appearance. The sight would be spectacular. A once ordinary yellow star has become an otherworldly jewel, a central white spark surrounded by a gauzy, multicolored veil of glowing gas, all set against the blackness of space. Over time, the nebula continues to expand and thin out. Each passing century, its glow diminishes as the gas spreads wider and the core gradually cools. Eventually, the lovely shapes and colors begin to fade. The expelled material drifts away into interstellar space, carrying with it the sun's essence, carbon from its heart, oxygen and helium, and other elements forged over its lifetime, all now free to mingle with cosmic clouds that will, in time, give rise to new stars and new planets. Future generations of celestial bodies may incorporate some of this very material, meaning a part of our sun will contribute to new cosmic creations. In the not-too-distant future, on the order of perhaps 20 to 50,000 years after its formation, the planetary nebula will disperse so much that it becomes invisible. The grand celestial artwork will have vanished, its glowing filaments dissipating into the surrounding darkness. What remains at that point is the lonely core of the sun, a white dwarf star cooling in the darkness, with no more nebula to light up around it. The sun's final performance has ended. All that persists is a small, dense star, the sun's final form, and the diffuse traces of gas flung far afield, mixing gradually into the wider galaxy. The sun's last glow has come and gone, a fleeting finale gracefully concluded. The once radiant sun has now become a white dwarf, a small, dense sphere about the size of Earth, composed mostly of carbon and oxygen. It shines with a brilliant white-hot light, but this light is the residual glow of stored heat, not the output of ongoing fusion. No more nuclear fires burn in its heart. The white dwarf is incredibly dense. The mass of roughly half the sun is packed into a volume only a millionth of the sun's original size. A spoonful of this white dwarf material would weigh tons on Earth. This tiny star is extremely hot at first, tens of thousands of degrees, and it will slowly cool and dim over an immensely long time. Around the white dwarf, the solar system is a shadow of its former self. The bright nebula has faded, leaving behind perhaps a gentle haze of gas that continues to drift outward. Any surviving planets, the outer giants and their moons, now circle a much smaller, fainter, central sun. From Jupiter's perspective, the sun that once dominated its sky has become a point-like star, shining with only a fraction of its previous warmth. The warmth and light that once bathed the planets is now only a ghostly remnant. If Earth had somehow survived the sun's giant phase, now a cold, airless rock, it would receive almost no light or heat. An eternal night, illuminated only by the faint pinprick of the white dwarf at the center. The white dwarf sun will continue to shine for billions upon billions of years, gradually fading. At first it will be bluish-white. Then, over many eons, it will cool to yellow, then red. In fact, as it cools, the sun's carbon core is expected to crystallize, essentially becoming an enormous cosmic diamond. Eventually, it will become a faint, dark ember, a hypothetical black dwarf. This cooling process is so slow that no black dwarfs are thought to exist yet in our universe's 14 billion year history. The sun's remnant will likely persist, shining ever more weakly for a time period that defies human comprehension. Trillions of years in the future, it may finally become too cold to emit visible light, blending into the darkness of space. And so, the life story of our sun reaches its quiet conclusion. From a fiery birth in a nebula, to a long golden age warming the dawn of life, to a gentle decline and a final brilliant flourish, it has traversed the full arc of stellar existence. In its death, the sun has returned its substance to the galaxy, the carbon from its core, the oxygen and other gases from its layers. All are now free to wander the interstellar medium. These ingredients will someday be part of new cosmic recipes, perhaps forming parts of future stars, future planets, maybe even future living beings. In this way, long ages from now, those materials will spark new life somewhere. And in that life, a faint memory of our sun will endure. As we reflect on this far future, there is a feeling of both melancholy and continuity. The sun, which for us is the very definition of permanence and reliability, is revealed to be mortal on the grandest timescale. Yet, nothing truly vanishes without a trace in the universe. The sun's energy and elements will resonate through time in other forms. Its atoms will drift through the Milky Way, possibly to be gathered into new suns, or to dust the surfaces of worlds not yet born. In that way, our sun will indirectly be a part of generations of stars to come. Now the sun's long day finally gives way to night. All that remains is a faint, cooling star, a lasting ember of what once was. The solar system that existed for billions of years is quiet and dark, illuminated only by the dim glow of the white dwarf, where a yellow sun used to shine. But in the silence of this cosmic night lies the completion of a cycle. The star that rose, shone, and set will inspire new dawns in the universe. The tale of our sun's final chapter is both an end and a beginning in the endless story of the cosmos. All of these transformations, the red giant's fury, the nebula's glow, the white dwarf's long fading, will unfold on timescales that dwarf human history. These events are billions of years away. For us who live under the sun's light today, such distant futures are almost beyond comprehension. Our star remains comfortably in its middle age and will not begin these final chapters for an extremely long time. Knowing the fate of the sun can be a humbling thought, yet it also can deepen our appreciation of the present. Every sunrise we witness, every warm ray of light on our skin, is a moment in a story that is still unfolding. The sun shines steadily now, giving life and light just as it has for ages past and will for ages to come. The thought that one day it will cease reminds us that even stars are not eternal. And so, the daylight we experience is all the more precious for its transience. One evening, as we watch the sun set in a blaze of colours, we might reflect that we are watching a tiny echo of the sun's far future. In that gradual fading of daylight is a symbol of the greater sunset that will eventually overtake our star. And yet, there is comfort in knowing that this cosmic sunset is unimaginably far off. Countless generations of humans, or their distant descendants, may come and go under the sun's warm glow before any noticeable change occurs. So we live in the sun's golden day, a day that will last for billions of years. The knowledge of the sun's life cycle invites us to marvel at the cosmic order. Stars are born, they shine, and eventually they rest. Some giant stars go out in a sudden supernova blaze, but sun-like stars like ours fade more serenely with a long farewell. Our sun is one of those countless stars following the same beautiful arc. By the era our sun meets its end, even our Milky Way galaxy may have changed beyond recognition, possibly merged with another galaxy, underlining that nothing in the cosmos stands unchanged forever. By understanding our star's final chapter, we gain a deeper reverence for the sunlight we enjoy and the life it sustains here and now. Tonight, when we see the pale stars emerge as the sun's light leaves our sky, we can gaze up and remember that our sun, too, is a star. And like all stars, it has its time. But until that distant day, when our sun's light truly dims, we greet each dawn with gratitude. The story of the sun's death is, in a way, a celebration of the cycle of life and change that governs the universe. And as we finish envisioning our star's distant final act, we return to the present, comforted by the familiar warmth of our living sun and the understanding that we are part of its story, a story still very much in its brilliant prime. In the silent depths of cosmic time, our sun is not the unwavering beacon it seems to us now. To human eyes and lifetimes, it shines with a steady light, rising and setting with reassuring consistency. Yet across eons, the sun is slowly changing. Deep within its core, hydrogen atoms fuse into helium, releasing energy that makes the star glow. Over millions upon millions of years, this ongoing alchemy very gradually increases the sun's brightness. Nothing dramatic announces this change. There is no sudden flare or obvious sign. But imperceptibly, year after year, the sun grows a little hotter, a little more luminous than before. Billions of years ago, when the sun was young, it glowed with far less intensity. In the dawn of the solar system, our star was perhaps only 2/3 as bright as it is today. Even then, that gentle sunshine nurtured a nascent Earth, though the planet had to hold its warmth beneath a thicker blanket of greenhouse gases. As the eons passed, the sun's fire strengthened. Within the stellar core, hydrogen fuel slowly diminished and helium ash accumulated, causing the core to contract and burn hotter. Each subtle inward shift of the core translated to a slight increase in the sun's outward brilliance. By the time life on Earth truly blossomed, the sun was already brighter than in its infancy, and it has never stopped brightening since. Even now, this increase continues on an inexorable course. Every few 100 million years, the sun's luminosity creeps upward by another small fraction. To our brief human experience, A single percent change is tiny, but given enough time, it becomes transformative. 1 billion years from today, the sun will shine nearly 10% brighter than it does at present. With each incremental rise in brilliance comes more heat pouring over the planets. Earth, bathing in this intensifying glow, will face a climate unlike anything in its past. What seems like a steady, eternal sun is in truth slowly turning up its thermostat, setting the stage for profound changes ahead. For now, Earth rests comfortably within the sun's habitable embrace, receiving a near-perfect dose of light and warmth. This balance has allowed oceans to sparkle and life to thrive under gentle skies. It feels timeless and unchanging to us, but it is, in truth, a transient equilibrium. Slowly, as the sun's output rises, this delicate harmony will be disturbed. Over geological timescales, the planetary thermostat will be pushed beyond its set point. Earth's climate will begin to shift, subtly at first, then more vigorously, striving to compensate for a sun that grows ever more intense. In time, those efforts will fall short, and the tranquil days of Earth's youth will give way to a harsher reality under a brighter sun. It is a humbling reminder that even the most enduring lights in our sky are subject to the inexorable flow of time. Earth's climate has always been a delicate conversation between sunlight and atmosphere. For now, that conversation is harmonious. Our planet orbits at just the right distance, close enough to bask in warmth, yet far enough not to scorch. Sunlight pours down, and Earth's air and oceans distribute the heat, fueling winds, rains, and gentle seasons. The result is a world temperate enough for liquid oceans and living creatures. Day after day, year after year, conditions remain within a familiar range. It is a balance so steady that ancient trees and tiny ocean plankton alike have flourished under the sun's largely unchanging gaze. But that balance has not been constant over geologic time. In Earth's deep past, the sun's rays were weaker, and the young Earth compensated with a thicker blanket of greenhouse gases to stay warm. Eons ago, dense carbon dioxide and methane in the air trapped what little warmth the faint sun offered, preventing the oceans from freezing solid. As the sun slowly intensified over billions of years, Earth's climate adjusted in turn. Excess carbon was gradually pulled from the sky and locked into rocks and seabed sediments, dialing back the greenhouse effect. Through this long dance, our world avoided both deep freeze and boiling heat, remaining clement enough for life to evolve and survive across the ages. Now, however, Earth is entering a new chapter of that climate dance, one that grows more challenging with time. The sun's subtle brightening continues, and Earth responds in whatever ways it can. When the air grows a touch warmer, chemical reactions speed up on the planet's surface. Rainfall leaches more carbon dioxide out of the atmosphere as minerals weather and sequester the carbon in stone. This natural process has long helped keep global temperatures in check, acting as Earth's thermostat. But a stronger sun forces that thermostat to work harder. In the coming hundreds of millions of years, carbon dioxide levels are expected to fall further and further as Earth tries to counter the mounting heat. Such a future poses a dilemma for life. Plants rely on carbon dioxide as their food, weaving sunlight and CO2 into sugars and oxygen. If CO2 becomes too scarce, plants begin to starve, not all at once, but gradually. Forests thin and growth slows. In some tens of millions of years, the lush abundance of plant life may start to diminish. Species that once blanketed continents could retreat, first from the heat and then from a lack of carbon dioxide to breathe. The world grows quieter and more barren as green vistas fade. Without dense forests and plankton blooms, Earth's atmosphere loses some of its oxygen replenishment and much of its vibrant energy. For animals great and small, these changes are catastrophic. Creatures struggle as their food chains wither. Ecosystems unravel, and one by one, many species vanish, unable to cope with the relentless heat and dwindling resources. Those that survive longer retreat toward the planet's cooler regions. As the low latitudes grow too hot and arid, many animals and plants migrate poleward or to higher elevations, seeking respite from the heat. The tropics, once teeming with life, fall silent and empty under the unrelenting sun. Life clings for a time in milder pockets near the poles or along cooler coastlines, but each year these safe havens shrink. Eventually, even the poles, once a sanctuary of ice and moderate climate, become inhospitable. The biosphere contracts to a thin shadow of its former self, before, ultimately, the advancing heat claims every refuge. Still, Earth's climate machinery struggles on, trying to stabilize the planet. Even as plant life wanes, the rocks and ocean continue absorbing greenhouse gases where possible. But the sun keeps imperceptibly turning up the heat. Average temperatures inch upward. Deserts expand as moisture evaporates more quickly in the hotter air. The poles, once locked in ice part of the year, remain unfrozen and wet. Storms become more intense as the energy in the atmosphere rises. On a warmer Earth, weather patterns shift in ways hard to predict. Regions that were once fertile and mild could become hot and arid. What was once a gentle balance becomes a teetering scale, ever harder to keep steady. Eventually, there comes a threshold that even geology and chemistry cannot counteract. The sun's output reaches a point where Earth's natural cooling fails. As the oceans and land absorb more heat, more water evaporates into the sky. Water vapor is itself a potent greenhouse gas, trapping even more warmth. In a reinforcing cycle, the warmer the air gets, the more moisture it can hold, and the more heat is locked in. With so much extra energy trapped in the air, the atmosphere grows more volatile. Storms swell to proportions never seen before. Overheated oceans give birth to titanic hurricanes that churn over entire basins, driving immense walls of cloud and vapor into the sky. These hyperstorms lash the continents with intense winds and unrelenting rain, but even they cannot reverse the warming. If anything, their violence pumps more heat and moisture into the upper atmosphere, accelerating the ocean's demise. In the wake of their fury, they leave behind flooded coastlines that quickly dry into new salt flats. The signs become undeniable. Shorelines begin to retreat as ocean levels drop, not because water is locked in ice. In fact, the polar ice is long melted, but because the water is slowly departing into the air and beyond. One can imagine standing on a future coastline and watching the sea draw back, not as a temporary low tide, but forever. A broad expanse of salt-encrusted sand stretches where waves once rolled in. Shells and the skeletons of fish litter the flats, exposed to the baking sun. The tide that for eons reliably returned now fails to come, leaving ships or rocks that were once submerged stranded high and dry. Each passing century, the water's edge slips farther away, and the ghosts of former bays and harbours turn to desert under the unrelenting sky. On a future Earth, baking under a harsher sun, shallow seas will be the first to vanish. Coastal areas might notice distant reefs becoming exposed, sandbars growing into broader flats under the sun. Fish and marine creatures would migrate with the shrinking waters, if they can. Some may find refuge in the deepening heart of the oceans for a time, but even the great abyssal depths cannot escape the inexorable loss. As surface waters warm, they expand and become lighter, stagnating above cooler layers. Eventually, even the deep sea starts warming as mixing continues year by year. The ocean's abyssal chill, preserved for millions of years, is gradually replaced with tepid water that has lost much of its dissolved oxygen. Marine life struggles. From tiny plankton to great whales, every layer of the sea feels the stress of rising heat and falling water. Perhaps one of the clearest harbingers of the ocean's fate is seen in the tropics. In those regions, the heat is most intense, and evaporation proceeds fastest. The air becomes heavy with moisture. Daytime skies might gleam white with high-altitude haze as water vapor accumulates in the stratosphere, a phenomenon foreign to the Earth we know. Normally, water vapor condenses and rains down long before reaching such heights. But now, with so much of it in the atmosphere, some water climbs higher, where the sun's ultraviolet light can break apart the molecules. Hydrogen, the lightest element, escapes Earth's grip into space. Oxygen left behind may form new compounds with the land, slowly oxidizing the soil and rocks. In this way, particle by particle, the ocean is literally bleeding off into the cosmos. Over millions of years, this loss becomes catastrophic. What starts as a subtle uptick in humidity evolves into a mass exodus of water. Seas recede from the continents, first slowly, leaving broad salt flats and parched coastal plains, then ever faster. The great ocean basins begin to expose their flaws. Imagine the Atlantic or Pacific drawn down to a fraction of its depth. The once hidden seafloor mountains laid bare under the dimming blue sky. Remaining water gathers in shrinking belts around the cooler poles, or in depressions where it can cling a little longer. Perhaps for a time, thin ribbons of water persist in the twilight of deep trenches, or at the poles during their long night. But the relentless heat ensures that even these last bastions cannot hold out indefinitely. As the seas vanish, so too does the life within them. Marine ecosystems collapse with astonishing swiftness. Coral reefs bleach and crumble on newly exposed seafloors, and schools of fish disappear as their waters turn to desert. Great ocean-going creatures have long since perished or fled toward the poles, only to find no refuge there either. In the end, even heat-tolerant microbes in the last briny puddles meet their demise when those pools boil away or grow too salty. The cradle of life becomes its grave, as the ocean's final generation flickers out. In the end, the Earth becomes a tale of two worlds. One it was, and one it is now becoming. The familiar blue marble transforms into a mostly dry beige-brown sphere. Where once there were vast, heaving blue oceans, now lie endless expanses of cracked, baked seabed. Salt crystals glitter where waves once danced. Former harbours and coastal cities, if any trace of them remains, overlook deserts stretching to a horizon that used to be sea. The air itself carries the memory of the oceans in its thick humidity. But with so much water vapour above, the heat at the surface only intensifies further, creating a vicious cycle that pushes the remaining water ever higher. Eventually, an irreversible point is crossed. The runaway greenhouse has fully taken hold. Water no longer returns to Earth in meaningful amounts. It simply rises and escapes. The cooling effect of evaporation is lost, and temperatures soar without check. At this juncture, the ocean's fate is sealed. Our planet, once misnamed as Earth, when it was truly the planet of water, has shed its azure veil. The transformation is profound, yet eerily quiet. No great convulsion marks the end of the oceans, just the long, slow evaporation under an uncaring sun. Venus's past is Earth's future. The two worlds, once so different, now converging in character. Earth begins to resemble that cloud-shrouded neighbour, an ominous preview of our planet's final form. Earth has now entered a realm that mirrors the fate of Venus. With the oceans gone and the water vapour dissipated to space, what remains is a heavy, choking atmosphere of carbon dioxide and nitrogen. Sunlight struggles to penetrate the dense cloud layers that enshroud the planet. Daytime on this new Earth is a dim orange glow filtering through yellowish clouds. The ground below is bathed in a perpetual twilight haze, even as temperatures soar to unimaginable heights. The air is thick and crushing. At the surface, the pressure is many times what we once knew, enough to burden every inch of any surviving structure with tons of force. It is an atmosphere that no creature could breathe, even if any life had somehow survived to this stage. This transformed world is eerily reminiscent of our sister planet, Venus, though situated farther from the Sun. Long ago, Venus too is believed to have possessed oceans and kinder skies, until a runaway greenhouse effect turned it into the hellscape it is today. Now Earth has followed that path. The surface temperature climbs well above the boiling point of water, exceeding 400 degrees Celsius in many regions, hot enough to liquefy metals like lead. Rocks on the ground glimmer with heat. Any trace of the former seas exists only as deposits of minerals and salts, now likely molten or metamorphosed by the extreme conditions. If some intrepid visitor were to stand on this Earth now, an almost impossible feat, they would find the landscape utterly alien and hostile, a far cry from the blue-green haven it once was. Clouds dominate the sky, but unlike the gentle white clouds of the past, these are dense banks laced with sulfur and acid. Volcanoes, no longer moderated by the presence of oceans or weathering, pump out sulfur dioxide and carbon dioxide unchecked. With no rain to wash them away, these gases accumulate, forming a toxic brew. Moreover, the very rocks of Earth start to give up their trapped gases. Minerals that once locked carbon dioxide into solid form begin to decompose under the relentless heat, releasing their carbon into the atmosphere. With no processes left to reabsorb it, this added CO2 further thickens the choking greenhouse blanket. The feedback loop has closed. Heat begets more greenhouse gas, which begets more heat in a runaway spiral. Occasional chemical lightning might flicker in the dense clouds, illuminating the gloom with silent flashes. But no rain falls. The water cycle as we know it has ceased. Any moisture released by volcanoes is almost instantly split apart in the searing atmosphere or lost to space. The once vibrant cycle of evaporation and precipitation is replaced by a stagnant, heavy shroud of greenhouse gases. On the ground, all is quiet and still in the thick heat. The great tectonic plates that once slowly shifted underfoot have ground to a halt. Without water lubricating the crust, the engine of plate tectonics ceases, locking the continents in place. The planet's interior still throbs with heat, and so volcanoes may periodically burst through the crust, but the moving, living geology of a watery Earth is no more. Instead, vast basalt plains and volcanic highlands are left to bake under the furnace sky, resembling the volcanic deserts we see on Venus. Dust and ash from eruptions hang in the heavy air, but even they settle slowly, weighted down by the dense atmosphere. Every trace of life's legacy is being eroded by this new environment. Organic molecules that once formed the basis of living things are unstable in such heat and reactive air. They break down into simpler compounds or burn away. The oceans that were the cradle of life are gone, and with them, the buffer that protected and nurtured life. Now, Earth's surface is effectively sterile. If any microbes somehow endured the escalating temperatures, they have finally met their limit. There are no oases, no shelters left, just a scorched world from pole to pole. The silence is profound. Where once the sounds of wind in trees, of waves on shores, and the chorus of living creatures filled the air, now there is only the faint hiss of a hot breeze sweeping over barren rocks. Even day and night have lost their meaning in this inferno. When the sun sinks below the horizon, the land remains searing hot, and the dense clouds still glow faintly with thermal energy. No cool night breeze ever comes. The air stays oven hot through the darkness. Indeed, the ground itself radiates a dull red light into the murk, like the embers of a dying fire, refusing to cool even without the sun's gaze. From space, this greenhouse Earth would appear cloud-covered and pale, much like Venus does. Little hint remains of the blues and greens of earlier epochs. Perhaps a slight reddish tint marks the sunlit edge, as the gigantic red sun looms in the sky. It is an ironic twist. The sun's increased power has made the Earth's surface darker under perpetual cloud, even as the planet itself is heated far beyond anything in its history. This world, once the jewel of the solar system, has transformed into a twin of Venus, a bleak, sweltering orb cloaked in thick clouds and mystery. In these echoes of Venus, scientists of a bygone age could find both vindication and sorrow. They long suspected that Earth might eventually become uninhabitable due to the sun's slow intensification. Now that prophecy is reality. The conditions so resemble those on Venus that one might imagine the two planets as twins separated by time. Venus shows us a picture of Earth's possible future, and now here Earth stands, indistinguishable from its once scorching sibling. The chapter of life and blue oceans on Earth has closed. Yet, even as our home world becomes inhospitable, the march of the sun's evolution shifts the possibility of life outward. The habitable zone, that tenuous ring of space where conditions allow liquid water, has moved beyond Earth. Where one world's tale ends, another's could begin, out on the fringes, where cooler realms now bask in warmth. One might picture this zone as a wandering spotlight, moving out from the sun and illuminating new stages for life. In its wake, behind the spotlight, lie the worlds it has left, overexposed and barren from too much heat. Ahead of it lie the worlds that still slumber in cold, awaiting their moment. It is a hopeful thought that as long as some part of the solar system falls within that nurturing light, the potential for life remains. The reality is also sobering. The spotlight does not linger indefinitely. Mars's moment in the sun will be fleeting, perhaps only some tens of millions of years, before the rising heat makes even that world uninhabitable again. So too with the outer moons. Their warm interval is short-lived, a brief cosmic summer in the midst of eons of cold. The spotlight moves on inexorably, and what becomes warm now will eventually grow overheated or freeze once more as the sun's evolution continues. For the life that originated on Earth, this moving target presents both peril and opportunity. In the distant future, perhaps life could migrate, or hitch rides to new abodes at the edge of the habitable zone, microbial spores carried by meteorites, or conceivably the deliberate efforts of an advanced civilization, might seed the soils of Mars or the oceans of a thawing moon. In this way, the legacy of life on Earth might continue, not on Earth itself, but on distant cousins of Earth warmed by a kinder sun. Should some far future intelligence be alive to face these changes, it would have to become a cosmic nomad, leaping from world to world as each in turn becomes habitable, carrying the torch of life onward. Such a journey would be unimaginably challenging, a race against the sun's advancing transformation. Yet it underscores a profound reality. The fate of life in the solar system is bound to the fate of the sun. To survive, life must follow the shifting warmth of our star, wandering wherever the habitable zone temporarily resides. We can imagine a timeline of refuge. First, the baton passes from Earth to Mars, a world that may enjoy a mild climate for some time after Earth has become hostile. Later, as the sun swells more, even Mars could become too warm, and the window of habitability might shift to the giant planet's moons, or even dwarf planets at the fringe. Perhaps in the farthest chapter, as the sun reaches its grandest red giant phase, worlds around Jupiter or Saturn bask in a comfortable glow. For however short a time that may be, life, if it can endure the transfers and find a foothold, could hopscotch outward, always chasing the transient, habitable zone. This outward journey of the habitable zone is a reminder that habitable is a moving target. It depends on the ever-changing sun. Once, Earth was perfectly placed. In the future, that precious placement drifts elsewhere. Even in the twilight of the sun's life, the principle remains. Somewhere at any given epoch, conditions might just be right for liquid water and possibly for life. The stage of life shifts slowly from planet to planet, moon to moon, like a lantern being carried through a darkened hall, illuminating one alcove after another. And now, as the sun's golden lantern moves outward, it lights up the red sands of Mars with new potential. A spotlight ready for the red planet to take center stage, if only briefly, in the long drama of the solar system. Mars, the red planet, has always tantalized our imagination with the possibility of life. For billions of years, it has been a frozen desert, its once flowing rivers and lakes long since turned to dry channels and ghostly shorelines. In its youth, Mars likely enjoyed a warmer epoch with rain and rivers carving its surface. Those waters eventually vanished as the planet froze. Now, in the sun's old age, Mars is being offered a brief second spring, an echo of that ancient warmth returning to the red planet. The thin air of Mars today can barely hold on to heat, and what water remains is locked in polar ice caps and underground vaults of frost. But as the sun's warmth spreads outward, Mars begins to change. The process is gradual, almost imperceptible on a human timescale, yet inexorable. Grain by grain, the carbon dioxide ice at Mars's poles sublimates into gas, thickening the atmosphere ever so slightly. Year by year, the average temperature inches up. With each passing millennium, the midday sun climbs higher above freezing on the Martian equator. The planet that was once an icy outpost is warming into something more hospitable. In those future Martian springs, we might see a newfound vibrancy on the ochre plains. Dark streaks appear along crater walls, where briny water, melted from subsurface ice, seeps out and trickles downhill for a few ephemeral weeks. Patches of ground that were iron hard with permafrost soften into mud under the stronger sun. Wisps of clouds form in a sky that grows denser and bluer as more atmosphere accumulates. Dust devils still dance across the deserts as they have for ages, but now they sometimes carry moisture, twisting into short-lived rain showers that wet the rusty soil before evaporating again. It's a marginal kind of warmth, nothing like the gentle rains of Earth's past, but compared to eons of deep freeze, it is a profound transformation for Mars. As decades bleed into millennia, Mars could approach a peak of habitability. Perhaps shallow lakes will collect in the lowest basins like Hellas Planitia during the warmest epochs. By this time, the sun in Mars's sky is brighter and more commanding, still smaller in apparent size than Earth's sun once was, but pouring down far more energy than Mars ever received before. Summer days in the Martian tropics might feel akin to a cool spring day on ancient Earth, at least at noon. In sheltered valleys, the thermometer could rise above the melting point of water for months on end. Any ice lurking just beneath the surface would thaw and refreeze seasonally, reshaping the soil and releasing gases into the atmosphere. Over time, a feedback could occur. More atmospheric CO2 leads to more warming, which releases more gas from the soil and polar caps. Mars's air, though still thin, becomes dense enough to support morning mists and perhaps occasional rainstorms. The sky that was once a butterscotch haze of dust could turn a pale blue tinged with gold as water vapor and thicker air alter the scattering of sunlight. Could life take hold in this fleeting Martian paradise? If Mars ever harbored life in its distant past, those organisms might have retreated into dormant states, spores or hardy microbes waiting out the deep freeze underground. Now, as liquid water reappears in transient pools and the temperature climbs, those ancient survivors could stir. Perhaps in a sheltered oasis, a patch of green film begins to coat wet rocks, algae-like growth feeding on sunlight and brine. If no indigenous life remains, Earth's own emissaries might fill the void. Hardy bacteria hitchhiking on meteorites or human probes could find a footing and multiply in the new Martian spring. Over thousands of years, a thin ecological web might spread in spots. Microbes in the wet soil, maybe simple lichens clinging to damp rock faces during the cooler twilight, surviving on the moisture of occasional rains. It would not be a lush Eden. Mars's revival is modest and precarious. The lakes would be shallow and seasonal, freezing in the long Martian winter, and perhaps vanishing for centuries during any particularly harsh climate swings. Any atmosphere gained is constantly at risk. Mars's gravity is light, and it lacks a global magnetic field, so the intensified solar wind of the evolving sun strips away gas, even as Mars tries to accumulate it. This tug-of-war between warming and atmospheric loss defines Mars's opportunity. For a while, the sun's gift of heat outpaces the loss, and the planet blossoms in its austere way. But the sun's inexorable increase does not stop. Eventually, what was a boon of warmth becomes an excess of heat. After reaching its comfortable apex, Mars too starts sliding toward a hothouse. The same process that doomed Earth will come for Mars, albeit starting from a colder baseline. The air grows thicker with water vapor from the new seas and ponds, amplifying the warming. Initially, this aids the climate, but beyond a point, it pushes Mars into its own version of a greenhouse fever. With the sun continuing to brighten and swell, the Martian atmosphere could tip into chaos. Water that once melted now boils off in the peak of summer. The nascent oases dry up or become hypersaline stews under a burning sky. If life had flourished in the brief Martian spring, it now must race against a rising inferno or retreat to refuges like the high latitudes or deep underground. Mars's era of habitability, though real, is temporary. The outward march of the habitable zone will leave it behind just as surely as it left Earth. Perhaps Mars enjoys a few million, or tens of millions, of years of relative mildness, a generous summer on the geologic calendar, but soon it will face the same fate: drying, heating, and sterilization. In the far future, as the Sun approaches its red giant phase, Mars may come to resemble a smaller version of what Earth became. A desiccated world, its brief seas evaporated, its skies choked with dust and carbon dioxide. The window will close, but for that brief cosmic moment, Mars could truly bloom, red sands dampened by water and possibly dotted by tiny colonies of life. It's a final grace period granted by the Sun, a last chance for life in the inner solar system, before the wave of habitability pushes even further out. And as Mars fades back into a lifeless desert, the focus shifts yet again, this time toward the giant planets and their moons, which await their turn in the warming spotlight. Far beyond Mars, the king of planets and its retinue of moons have long dwelled in deep cold. Jupiter and Saturn, with their orbiting families of icy satellites, were once places of perpetual frost and darkness. But as the Sun continues to swell and brighten, even these distant regions feel the change. The transformation is most dramatic on the large moons that orbit these giants. Worlds like Europa, Ganymede, and Callisto around Jupiter, and Titan around Saturn, begin to awaken from their frozen slumber. Take Europa, Jupiter's enigmatic moon, with a hidden ocean beneath its ice. For countless millennia, Europa's surface has been a crust of water ice as hard as rock, crisscrossed by cracks where a bit of liquid from below sometimes oozed out and froze. Under the red-tinged sunlight of the future, Europa's ice starts to soften at the surface. The Sun, now much more luminous, shines on Europa with an intensity that can nudge the thermometer near the melting point at local noon along the equator. The top layer of ice turns slushy in places, pooling into ephemeral puddles that later refreeze when night falls. Geysers of water that once sprayed sporadically from Europa's south polar fissures now erupt more vigorously, fed by an ocean invigorated with heat from above. A tenuous mist of water vapor forms a thin atmosphere, hazing around Europa each day and partially dissipating at night. If one were to look up from Europa's surface, they would see a sky tinted pale blue-grey from the icy vapor, and a dim red sun hanging where once it was merely a distant point of light. If one could stand on Europa's surface during this epoch, the scene would be otherworldly. Above, the giant face of Jupiter hangs in the sky, its once muted bands now gleaming with bright white clouds formed by the red giant's heat. The Sun, much larger now, but softened to a dusky crimson orb, lights Europa's landscape in perpetual twilight. A thin fog of sublimated ice hugs the ground, blurring the stars and casting halos around the distant, swollen Sun. The ice underfoot is slick and damp, giving hints of the ocean stirring below. It is a fleeting moment of mildness on a moon that had known only deep cold. On Ganymede and Callisto, Jupiter's other large moons, a similar thaw begins. Ganymede, the largest moon in the solar system, and itself possessing a once frozen ocean deep below, develops patches of surface frost that melt under the elevated Sun. Ganymede even has a weak magnetic field of its own, offering a slight protective bubble to hold a fledgling atmosphere a bit longer than Europa can. As sunlight penetrates its icy plains, gas seeps out. Oxygen from split ice molecules, perhaps a hint of water vapor. Inky black crater floors that never saw liquid now glisten with a rime of moisture. Callisto, heavily cratered and ancient, warms enough that the rims of some sunward craters darken with dampness each afternoon. These moons begin to trade their eternal ice for a brief, breathy exhalation of atmosphere. Around Jupiter itself, the entire system takes on a changed aspect. The giant planet's cloud tops grow warmer and start to sport brilliant white water clouds, thanks to the influx of water vapor escaping its moons. Jupiter, reflecting more sunlight with these new clouds, shines even brighter in the sky of its moons, creating an interplay of light that both warms and illuminates them. Shift focus to Saturn's domain, and the changes are arguably even more startling. Titan, Saturn's largest moon, has always been a world of paradox. Frigid, yet possessing a dense atmosphere thicker than Earth's, with lakes and rivers not of water, but of liquid methane and ethane. As the sun's heat intensifies and reaches Saturn's orbit, Titan's orange haze begins to burn off. The methane in its air that once formed a smog is baked away by the stronger sunlight, and the hydrocarbon lakes at Titan's poles evaporate and vanish. In their place, something remarkable occurs. Titan's surface, composed largely of water ice, warms enough for that ice to melt. For the first time in Titan's history, liquid water can exist on its surface. The thick nitrogen atmosphere ensures that when Titan's ice melts, the water remains liquid for a while instead of instantly sublimating. Titan could briefly become a water-rich world, its arid river channels filled with flowing H2O instead of methane. Imagine standing on Titan's plains during this epoch. The air is still dense but clearer, tinted golden by sunlight. In the sky, Saturn looms faintly through the thinning haze, while a swollen red sun pours heat onto a landscape where water trickles and pools. Overhead, bright white clouds of water gather in Titan's sky, and for the first time in its history, warm rain begins to fall. These raindrops, distilled from melting ice, patter onto Titan's dunescapes and into the basins that once held liquid methane. In the dense air, they fall slowly, almost gently, forming transient puddles and lakes of actual water. As the clouds part, one could even imagine a faint rainbow glimmering through Titan's amber haze, a sight utterly foreign to this moon until now. Titan's rich inventory of organic molecules, the legacy of eons of chemical stew, now mix with liquid water, potentially sparking chemical reactions that were never possible in the deep freeze. For a short golden age, Titan might become a cradle of warm chemistry, a potential incubator for life, where before there was only cold and inertness. Even smaller moons feel the sun's new touch. Enceladus, a tiny moon of Saturn, famous for its icy geysers, is pushed into overdrive. Its south polar jets of water erupt with furious intensity as the subsurface ocean responds to the extra warmth. Enceladus's geysers may loft plumes so large that they form a transient atmosphere around the moon each day. But with such weak gravity, Enceladus cannot hold on to this gift. Much of its water escapes, creating a glittering halo of ice crystals that might catch the sunlight like never before. Other moons, too small or too airless to retain vapors, simply vent their ices and gradually shrivel, surrendering their ancient ice to space. In this epoch, the outer solar system transforms from a realm of darkness and ice to one of water and vapor. Icy surfaces darken with meltwater, and thin clouds hug moons where once there was only vacuum. If life lurks in the subsurface oceans of Europa or Enceladus, the improved conditions might allow it to expand its range, perhaps venturing closer to the surface or thriving in newly warmed niches. On Titan, the ingredients for life, water, warmth, and complex chemistry, combine in a way they never have before, offering a tantalizing, if short-lived, possibility that life could spark or flourish there. These moons, long in the shadow of their parent planets and far from the sun, finally step into the spotlight of habitability. Yet, like all things in this unfolding cosmic drama, the awakening of the moons is transient. The sun's red giant phase, though monumental, is not stable. It will reach a peak and then fade. And before that happens, the conditions on these moons may also tip from hospitable to inhospitable. Europa's newfound atmosphere may soon collapse as its surface ice dwindles, or as the sun's radiation strips the escaping gases away. Titan's balmy interlude will come to an end as its water either escapes or refreezes when the heat becomes too intense or later subsides. The warm seas on its surface could evaporate into space or fall back as snow in a future cooling. The outer planets' kingdoms, once places of perennial frost, enjoy their brief summer and then march on to a different fate. For now, however, one can marvel at the picture. A solar system, where even the far-flung moons wear a veil of clouds and perhaps host liquid water. The sun's influence has indeed expanded dramatically. Worlds that were once afterthoughts in terms of habitability now briefly hold center stage. As these distant moons bask in the glow of an engorged sun, the entire architecture of the solar system feels the stars' growing reach. Orbits may shift minutely outward as the sun sheds mass, and the balance of energies between planets and star is rewritten. The giant planets and their moons, warmed and stirred, hint at how profoundly the sun's late-life changes affect every corner of its domain. And as the system rearranges itself under the red sun, we turn to consider those very shifts, in gravity, in orbits, in the sun's own energy output, that accompany the star's expansion into a true giant. The sun's metamorphosis into a red giant does more than just alter the climates of planets. It also rearranges the very structure of the solar system. As the sun swells and sheds its mass in great stellar winds, its gravitational grip on the planets weakens. The once steady orbits begin to expand outward. All the planets slowly drift away from the sun, like dancers taking a step back from a partner who has grown too overpowering. This change happens gradually at first, then accelerates as the sun loses more mass in its later stages. Over time, Earth, or the cinder that remains of it, inches farther from the sun, perhaps moving millions of kilometers outward. If Earth is still intact during the sun's gigantic phase, it might find itself orbiting at a distance that was once on the outer fringe of the habitable zone. Ironically, a cooler orbit, arriving far too late to save it. Mars too spirals outward, along with the gas giants and their moons. The whole cosmic ballet opens its formation, each planet receding from the sun's furnace as if seeking relief. For the inner planets, these orbital shifts carry dramatic consequences. Mercury, the innermost world, is almost certainly gone, the first to fall into the solar fire. For Mercury, the end comes swiftly and almost without fanfare. As the sun's bloated sphere reaches its orbit, the tiny planet is engulfed and vaporized within days, its substance absorbed into the sun's outer layers. Venus likely shares a similar fate, falling victim to the advancing solar flames as well. Venus, larger and slightly farther out, resists only a moment longer. The expanding solar photosphere blasts away Venus's thick clouds and then swallows the planet whole. Two inner worlds that once knew the sun's gentle light are simply erased, leaving no trace but a ripple in the sun's fiery envelope. Earth's ultimate destiny is a razor's edge scenario. Some calculations suggest that as the sun loses mass and its pull weakens, Earth could migrate outward just enough to avoid being completely swallowed by the swollen sun. In that scenario, our planet would survive in body, if not in spirit, orbiting a bit farther out than before. Other calculations foretell a less merciful end, with Earth dragged into the red giant's atmosphere and vaporized after all. Either way, by this juncture, Earth is no more than a barren rock or a memory. The distinction between a consumed Earth and a charred, drifting Earth is subtle in practical terms. In both cases, the cradle of life is destroyed. With Mercury and Venus gone, and Earth effectively out of the picture, Mars may become the innermost planet of the solar system for a time. It circles a much altered sun on a path that has also expanded. A Martian year grows longer as the planet slips farther out, tracing a wider ellipse through space. The lengthening of orbits is a silent chronicle of the sun's declining mass. Time itself, measured in years, stretches out for the remaining planets. Any hypothetical clock on Mars marking the years would tick ever more slowly, as if the dying sun is putting the brakes on the solar system's clockwork. As the planets move outward, the finely tuned gravitational resonances that once governed their motions begin to shift. The delicate balance of the inner solar system is already upended by the loss of its innermost worlds. In the outer system, Jupiter and Saturn also feel less pull from the Sun and drift to slightly higher orbits. This can alter their interactions with each other and with lesser bodies like asteroids and comets. Some asteroids might wander out of their old stable belts, freed from the Sun's firmer grip, embarking on new paths through space. The distant Oort cloud of comets, loosely bound to begin with, might see some members gently released to drift off into interstellar space, no longer captive to a sun that has slimmed down. The increase in the sun's luminosity and size also changes the distribution of energy across the solar system. The frost line, that invisible boundary where it was cold enough for volatile ices to remain frozen, has been pushed outward drastically. In the youth of the solar system, the frost line lay out near Jupiter. Now, under the red giant sun, even Pluto lies well inside the zone of warmth. Ices that have been stable for eons on distant dwarf planets and comets begin to vaporize. One could imagine Pluto in this era. Once a frigid outpost of nitrogen ice and methane frost, Pluto now basks in roughly the amount of sunlight Earth once enjoyed. Its surface ices heat up and sublimate, wrapping Pluto in a thin, ephemeral atmosphere far more substantial than the tenuous haze it sports today. Geysers of nitrogen might erupt from its surface as it warms, and the sky of Pluto could turn a ruddy hue, filled with escaping molecules lit by the red sun. Dozens of other Kuiper belt objects, frozen mini-worlds at the solar system's edge, undergo similar transformations. They begin to sprout comas and tails like comets without ever leaving their orbits, shedding their ancient ice in the newfound sunlight. The solar system's fringe, once dark and inert, comes alive with a feeble glow of outgassing frost. This massive redistribution of heat and light means that the balance of energy each planet receives versus what it radiates back to space has changed fundamentally. In the planets that remain, equilibrium temperatures shift. Jupiter's cloud tops grow balmier. Neptune's sapphire blue atmosphere warms enough to lose some of its frigid austerity, and the littlest icy bodies glimmer with transient atmospheres. The star that was once a concentrated beacon of light at the center has become a bloated, diffuse orb dominating much of the sky for those planets still near enough to see it as a disk. Its light is redder now, skewed toward the infrared, meaning it penetrates differently and is absorbed in different ways by planetary atmospheres. On worlds with clouds or haze, the sky colors shift. For instance, a world like Titan transitions from an orange murk lit by a tiny sun to a brighter, hazy daylight under a huge crimson sun, altering how light filters through its air. Throughout this grand realignment, a vast stellar wind carries matter outward from the sun. This flood of particles not only carries away mass, altering gravity, but also electrifies the space around the planets. Magnetic fields around planets like Earth, if it still had one, and Jupiter are blasted by an onslaught of charged particles far more intense than before. Auroras would have danced fiercely on those worlds, had anyone been there to witness them, painting the skies with ghostly light as the solar wind peaked in strength. The heliosphere, the sun's domain of particle influence, balloons outward under pressure from within, its boundary perhaps expanding as the dying sun's influence reaches farther, until the sun begins to lose its power and everything contracts again. The solar system, once a tight-knit family of planets orderly circling a vibrant star, now finds itself a dispersed collection around a bloated, faltering sun. The old certainties of orbital distances and year lengths are undone. And yet, even in this flux, there is a strange temporary stability. The planets continue to orbit, albeit farther out, and the system carries on, changed but not destroyed outright, save for those inner casualties. This morphed configuration will itself be short-lived in cosmic terms. The sun has not finished its convulsive changes. Soon will come the climax of its expansion, the true red giant moment when it reaches maximum size and luminosity. In that fiery crescendo, whatever parts of the inner solar system remain will face their ultimate test. But even as we brace for that finale, remember that what has been set in motion, the drifting planets, the evaporating comets, the red skies of distant moons, are all part of the ongoing dialogue between a star and its companions. It is the solar system's way of responding to the star's grand last act, adjusting and shifting under the sun's expanding influence, setting the stage for the next movement in this cosmic symphony. In the heart of the sun, the fuel of ages is nearly spent. For over 10 billion years, hydrogen fusing to helium has powered the star's steady glow. Quietly and relentlessly, helium ash has accumulated in the core, like ashes in a long burning fire. Now that fire falters, the hydrogen in the sun's innermost core is exhausted, leaving inert helium packed at the center. With no fusion to support it, the core begins to contract under its own immense weight. This contraction raises the core's temperature dramatically. Unseen from the outside, a profound change is underway. Shells of hydrogen around the core ignite in fusion, trying to compensate. The sun, which for eons changed only gradually, is about to enter a period of rapid transformation. At first, the sun's outward appearance shifts subtly. The increased energy from the shell fusion pushes against the overlying layers, making them swell. Over a few 100,000 years, the sun's circumference grows, and its color starts to drift from golden white to a lighter yellow, then toward a tinge of orange. Astronomers of an earlier time, had they been there to observe, might notice the sun's spectrum changing, the star looking a bit cooler even as it shines more brightly overall. The solar diameter expands slowly at first, so that 1 billion years after the present, it might be tens of % larger than today. But these changes are only the prelude. Once the core contraction reaches a critical threshold, the process accelerates. The sun, long stable, begins to balloon outward at an astonishing rate by cosmic standards. In a span of just a few million years, an eye blink next to the sun's long life, the star's radius multiplies. What was once calculations and far-off prophecy now becomes reality. The sun is evolving into a red giant. Its outer layers, now far-flung, cool down in temperature, giving the bloated sun a ruddy hue. The brilliance of the sun does not diminish, however. It intensifies. The surface area has grown enormously, and despite each square meter emitting less heat due to the cooler temperature, the sheer vastness of that surface means the total light output soars to many times what it was. To any surviving worlds or observers, the sun's transformation is both beautiful and terrifying. It dominates the sky in a way never imagined. From whatever remains of Earth, or from a vantage on Mars, the sun now looms colossal, a deep orange-red disk that spans a significant portion of the sky, flooding the landscape in a coppery twilight, even at high noon. During daytime, on a distant moon of Jupiter or Saturn, the sun no longer appears as a small white orb, but as a great, fiery canopy overhead. Its light, though tinted red, is so strong that it washes over the entire horizon. Shadows fade and soften under the diffuse, giant sun. The night has all but vanished for inner planets. Twilight reigns even on the side of those worlds turned away from the sun, as the enormous star's glow filters through space. The solar system is lit as never before, the darkness pushed to the very edges of interplanetary space. Inside the sun, chaos and creation go hand in hand. As the hydrogen shell burning intensifies, the helium core grows hotter and denser until, in a moment of stupendous release, helium itself ignites in what astronomers call the helium flash. This event is largely smothered by the sun's opaque layers, but it marks a new chapter. The sun starts fusing helium into carbon in its core, providing a temporary reprieve against further collapse. The outward effect is to slightly stabilize the sun's expansion. But by this point, the sun is fully a red giant star. It has reached a size and luminosity unimaginable in its younger years. The quiet changes that took so long have now erupted into a dramatic climax. The sun is hundreds of times its original size, a giant swollen sphere seething with convective currents, gently pulsating as it adjusts to its new state. Its surface, once a relatively calm yellow photosphere, is now a cooler, darker expanse, mottled with gigantic star spots and brilliant flares. Solar winds of unprecedented strength stream off its surface, carrying away the star's outer material into space. The sun has never been more luminous, but it has also never been more unstable. Yet, in a cosmic sense, there is an eerie tranquility to this scene. From afar, a red giant star is a common sight in the galaxy, a star in its sunset years, glowing placidly. Up close, however, for any who could witness it, the change is monumental. The transformation from a stable main sequence star to a bloated giant has been gradual and inexorable, like a tide rising over millennia and then suddenly sweeping in with a final grand wave. The sun's path toward red giant has been paved with slow, almost imperceptible changes that gathered momentum until they became overwhelming. What was once theory is now spectacle. Our sun, the star that nurtured all the life and patterns of the solar system, has become something wholly different. Its gentle warmth is replaced by an intimidating radiance. Its formerly small, bright disk is now an engulfing canopy of light and heat. The solar system must reckon with a very different central beacon. Planets that remain find themselves deep inside the star's extended atmosphere, or baking under its intense proximity. Moons that once shivered in darkness are drenched in ruddy light. Everything has changed. As the sun settles into its red giant grandeur, a moment of pause might be imagined. The star has reached the apex of its bloated form, a pinnacle that it will not maintain for long. The core's new helium fire will burn briefly, in stellar terms, before the sun faces the next stages of its demise. But for now, this is the climax of the sun's expansion. The long, quiet build-up has crescendoed into a towering giant. In the next movement of this cosmic saga, we will witness what becomes of the sun at the height of its red giant power and the aftermath of that final blaze of glory. The stage is set for the final chapters in the life of our star, as the red giant begins to reveal the destiny that awaits beyond the giant's embrace. Already, the sun's enormous form is growing unstable. It pulsates gently, foreshadowing greater convulsions to come. Before long, it will begin to peel away its outer layers, casting them off into space in great shimmering waves. When it does, the sun will create a final cosmic spectacle, a glowing nebula of its own former substance, expanding outward and leaving behind only the small, intensely hot heart of the star. That, however, is a scene for the next act of this story. For now, the sun presides over a dramatically altered solar system as a crimson giant, a glorious, if fleeting, pinnacle before the quiet of its stellar twilight. Deep inside the sun's heart, a quiet change is taking place. For ages untold, our star's core blazed steadily, fusing hydrogen into helium and holding back the crush of gravity in a perfect balance. But now, after billions of years of shining, the sun's supply of hydrogen fuel is nearly exhausted. The nuclear reactions that once burned so brightly at its core are fading, leaving behind a growing core of helium ash. With every passing eon, the balance the sun maintained for so long begins to shift. As hydrogen dwindles at the center, the outward pressure that once balanced the sun's core begins to fade. With too little force pushing outward, the core can no longer support the immense weight of the sun's own layers. The heart of the sun begins to collapse inward under its own gravity, pulling its matter into a tighter and tighter space. This contraction is slow, but inexorable, a drawn-out surrender to gravity's unyielding pull. As it shrinks, the core grows even hotter, tens of millions of degrees and rising, under the relentless squeeze of gravity. Deep within, the contracting core is now a dense ball of helium that cannot yet burn. But as the core's temperature climbs, the effects ripple outward. Just above the core lies a shell of unburnt hydrogen, now growing ever hotter as the core continues to contract. It is here, in this thin envelope around the core, that the sun's next chapter of fire will soon ignite. In time, the core's rising heat ignites a new kind of fire just outside its boundary. The shell of hydrogen surrounding the helium core suddenly comes alive with fusion. In that narrow region, hydrogen atoms begin fusing furiously into helium, releasing an immense surge of energy. A brilliant burning layer now wraps around the dormant core, like a glowing halo inside the sun. This development gives the sun a new lease on life, but in a radically altered form. The sun's energy production is now layered, an inert helium core at the center, and an intensely burning hydrogen shell wrapped around it. With each passing moment, the shell creates more helium, which falls onto the core below. The core grows heavier, shrinking further and heating even more, which makes the shell's fusion burn hotter still in a self-reinforcing cycle. The flood of new energy from the shell pushes against the sun's outer layers, forcing them to expand outward. The sun begins to swell in size, growing larger and more luminous as time passes. Its outer gas layers cool as they spread out, changing the star's color to a rich orange-red hue. The once modest sun is on its way to becoming a bloated giant. In the early stages, the sun's swelling was gradual and subtle. It passed through a subgiant phase, expanding only moderately and taking on a more orange hue. But as the shell fusion intensified, this expansion accelerated dramatically. The sun's outer layers pushed outward faster and faster, and its transformation into a true red giant became unmistakable. The sun has now become a true giant. What was once a yellow-white orb of modest dimensions has bloated into an immense sphere hundreds of times wider than before. It has swelled outward until its edges reach close to Earth's orbit, roughly 150 million kilometers from its center. The paths of Mercury and Venus, once well outside the sun's surface, now lie deep inside the sun's vast, expanded body. As the sun's size grew, so too did its brightness. The red giant sun is thousands of times more luminous than it was in its prime. Every second, it floods the solar system with an enormous output of energy, far greater than in its former life. Even though its surface glows cooler and redder now, the sheer expanse of that surface means the sun's total light has multiplied dramatically. For all the sun's enormous bulk as a red giant, much of that bulk is surprisingly diffuse. The outer regions of the star are not solid or even dense gas, but more like a tenuous cosmic haze. A spacecraft venturing to where Mercury once orbited would actually find itself inside the sun's outer atmosphere, yet the gas there would be nearly as thin as a vacuum, though searingly hot. Only much closer to the sun's core would the atmosphere thicken into the dense, blazing plasma that defines the star's fiery heart. The once familiar sun has utterly transformed. It now looms as a gigantic red beacon dominating the skies of every planet. Its presence colors the heavens of the surviving worlds in hues of crimson and copper. Throughout the solar system, night and day are forever changed under the reign of this red giant sun. On Mars, daylight is dominated by a massive red sun that spans a huge portion of the sky. Instead of a small, brilliant disk, the sun appears as an overwhelming ruby glow overhead, casting a rusty light over the barren Martian deserts. Mars's thin, dust-filled sky is bathed in a dim red twilight, even at high noon. Shadows become faint and diffuse under this sprawling sun, as its light pours down from a broad swath of the heavens, rather than a single point. The sunset on Mars lasts much longer now, with the sun's enormous disk taking hours to slip below the horizon. Even after it finally disappears, the sky stays aglow with a ruddy twilight, as fine dust in the air reflects the sun's lingering light. On Jupiter, a world that once lay in distant cold, the sky is now dominated by the swollen sun. For an observer drifting among Jupiter's cloud tops, the sun would loom vast and heavy, dozens of times larger than it once appeared. From Jupiter's roiling cloud bands, the sun appears as an immense dusky disk, painting the planet's banded atmosphere in gold and crimson hues. Daylight on Jupiter, once faint and twilight-like, is now many times brighter, suffusing the turbulent clouds with a coppery glow. The great storms of Jupiter, its belts and the great red spot, churn under a perpetual red twilight, an endless alien sunset across the giant world. At Saturn, the spectacle is equally surreal. The planet's famous rings, normally bright and icy, now shine with a copper-red luster under the giant sun's rays. Saturn's pale golden atmosphere is tinted a deep orange, and a dim red daylight envelops the planet. If one could stand on Saturn's rings, they would see the ice there glitter in coppery hues, and the gigantic red sun would hang in the sky, casting diffuse bronze shadows across the ring plane. The once distant sun is now a prominent, swollen orb in Saturn's sky, turning the scene into one of silent, otherworldly beauty. Even at the outermost edges of the solar system, the change in the sky is dramatic. On a distant dwarf planet like Pluto, which once knew the sun only as a bright point of light, there is now a small but discernible disk of soft red glow in the sky. Pluto's icy surface is illuminated by a perpetual red twilight, bright enough to cast shadows where once there were none. The deep dusk that reigned at the solar system's fringe has given way to a gentle red day, as the dying sun's light reaches even the farthest frozen worlds. In this faint red daylight, Pluto's frosted plains gleam and send a ghostly mist into the thin air, a temporary atmosphere born of the newfound warmth. For the outer planets, the red giant sun is a breathtaking spectacle, a distant dawn after ages of night. But closer to the sun, this transformation brings only doom. The inner worlds are being scorched by unyielding heat and light. Earth, our once blue sanctuary, has entered its final desperate days beneath the swollen sun. Earth has become a world on the brink of annihilation. After eons of flourishing under the sun's life-giving light, our planet now receives only a merciless blaze. Long before the sun reached its red giant peak, our planet's oceans had boiled away into space. Now, under the giant sun's furnace-like heat, Earth's surface is scorched, dry, and barren. The air itself has been stripped off, blown away by intense solar wind and searing radiation. All that remains is a broiling, airless rock, glowing faintly with the heat of its own destruction. On what remains of Earth's surface, if one could stand there, the view would be otherworldly. With no atmosphere, the sky is jet black even at noon, and across that darkness sprawls the gigantic face of the red sun. The sun's vast disk covers a huge portion of the heavens, pouring its fiery crimson light directly onto the barren ground. The ground itself glows dimly red from the searing heat, and no sound or breeze stirs in the airless, deadly stillness. With the sun so near and enormous, Earth is racked by powerful tidal forces. The sun's gravity pulls one side of Earth more strongly than the other, causing the planet's crust to heave and quake. Whole continents shudder, and volcanoes erupt from the stress, spilling lava that quickly cools under the relentless glare. The once solid ground softens in the extreme heat, and parts of Earth's surface begin to melt into molten seas of rock. As Earth orbits perilously close to the swollen sun, it struggles to cling to its path. The sun's extended atmosphere brushes against Earth, creating drag that slowly pulls the planet inward. With each passing year, Earth spirals a little closer to the giant star. Before long, the planet will be overtaken, either torn apart by gravity or swallowed whole into the sun's fiery embrace. Long before this final cataclysm, Earth's biosphere had already withered away under the sun's escalating heat. No life remains to witness these final agonies of Earth. The great forests and oceans that once adorned our world are long gone, and even the very rocks now glow with heat. The achievements and monuments of humanity have crumbled or vaporized in this hellish environment. No trace of our civilization endures. A planet that was once vibrant blue and green has become a charred ember, indistinguishable from a scorched cinder. Earth's long history has reached a silent, lethal end under the glare of the dying sun. Earth's fate is sealed, but it was not the first world to fall victim to the dying sun. Closer to the sun, Mercury and Venus have already met their demise. Those inner planets plunged into the sun's bloated sphere earlier in the red giant phase, disappearing in flames. Their destruction foreshadowed what is now coming to pass for Earth. Mercury, the innermost planet, was the first to be claimed by the expanding sun. As the sun's growing body swelled past Mercury's orbit, the tiny world was completely engulfed. Mercury's surface, long seared by intense heat, melted and vaporized within minutes of slipping inside the sun's fiery layers. In its final moments, Mercury disintegrated into glowing vapor, its substance absorbed into the sun's burning envelope. As Mercury met its end, one can imagine the final scene on that scorched world. The sun's glowing wall of fire filled Mercury's sky from horizon to horizon. Mercury's grey, cratered surface began to glow white-hot as the solar plasma flooded over it. In moments, the rocks, metals, and dust of Mercury vaporized into a mist, and the tiny planet was no more, swallowed silently into the sun. Not long after, Venus met the same fate. The second planet, once cloaked in dense clouds, saw its atmosphere stripped away and its surface turned to glowing rock under the intensifying heat. As the sun's swollen photosphere reached Venus's orbit, the planet tumbled into the stellar inferno. Venus, larger than Mercury, took a little longer to break apart, but it too was utterly consumed. Its shrouding clouds, molten plains, and very crust were all swallowed by the hungry sun, leaving not a trace behind. As Venus succumbed to the sun, its fate was equally dramatic. The thick cloud layers that once enshrouded Venus were blasted away as the sun drew near, exposing its glowing orange surface. The air on Venus, heavy with carbon dioxide, superheated and rushed off into space in a final exhalation. In Venus's last moments, its lead-melting surface began to boil and vaporize. The planet that once gleamed as Earth's morning star vanished into the solar inferno, its substance absorbed without a trace. The demise of these planets was swift and silent on the cosmic stage. As each world slipped beneath the sun's surface, it sent brief ripples through the stellar flames. There may have been a momentary brightening, or a plume of plasma expelled as the sun absorbed the planet's material. But soon, the red giant settled back into its massive calm, hardly noticing that two worlds had been devoured. In the aftermath, nothing remained of Mercury or Venus except faint traces of their substance mingled in the sun's atmosphere. Two once distinct worlds, one a tiny airless rock, the other a cloud-veiled furnace, were now gone forever. For billions of years they had circled the sun, and in a matter of moments they were gone. The inner solar system had lost these planets entirely to the fires of the sun. Their empty paths around the sun stood as silent testimony to the beginning of the end for the inner solar system. With Mercury and Venus gone, and Earth in ruins, the architecture of the solar system was irreversibly altered. The sun is shedding mass at a prodigious rate in this red giant phase. By the end, it will have lost nearly half its mass. loosening its gravitational grip. As the sun's pull weakens, the surviving planets gradually migrate outward into wider orbits. The whole system expands in scale, slowly reconfiguring under the changing gravity of the dying sun. The entire solar system swells in scale. Neptune, which once orbited at about 30 times the Earth-Sun distance, gradually drifts out to nearly twice that distance. Each of the gas giants settles into a more distant orbit than before, expanding the boundaries of the sun's domain. With the sun's hold weakened, the delicate harmony of planetary orbits is disrupted. Their paths slowly shift and wobble over millennia. Some smaller bodies, such as far-flung comets and asteroids, may even wander off into interstellar space, no longer tightly bound to the sun. Mars, now the closest planet to the sun, is transformed as well. Once a frigid desert world, it becomes intensely hot under the red giant's glare. Mars's polar ice caps vaporize entirely, fueling dust storms that sweep across its scorched, rust-colored plains. The thin Martian atmosphere, superheated and swollen, escapes into space, leaving behind an even more barren, oven-dry globe. The shifting orbits are accompanied by drastic environmental changes. Worlds that were once locked in deep freeze now receive far more warmth from the bloated sun. The habitable zone, the region where liquid water can exist, migrates outward, sweeping across parts of the outer solar system. Frozen moons and distant dwarf planets thaw under the red glow, their icy surfaces sublimating and even pooling into brief, shallow lakes of liquid. For a short epoch, places that spent eons in darkness now bask in gentle warmth, perhaps nurturing temporary seas under the giant sun's light. Even ancient comets at the fringes of the solar system begin to stir, their frozen bodies sprouting faint tails as they feel the growing warmth of the red sun. Moons that were once frozen solid are now coming alive in the warmth. The icy crust of Jupiter's moon Europa begins to crack and melt, exposing the dark ocean that lay buried for eons. Titan, Saturn's haze-shrouded moon, warms until its frigid methane lakes evaporate into its thick orange sky. Even distant Pluto acquires a thin atmosphere as its frozen nitrogen plains vaporize under the red giant's rays. Yet this brief spring in the outer solar system is destined to end. The red giant phase, for all its grandeur, is only temporary in a star's life. Before long, the sun will cast off its outer layers and begin to fade, and this newfound warmth will vanish. The distant worlds that thawed under the red glow will freeze again, their momentary summer ending as quickly as it came. The sun's life as a red giant is not one of quiet stability. The bloated star has become highly variable, almost as if it were breathing. Over spans of years, its outer layers slowly expand and contract in a steady rhythm. The sun brightens and dims in great cycles, undergoing vast cosmic seasons in its old age. As the sun pulsates, each expansion and contraction is enormous. At times the star swells beyond its average size, then later it shrinks back slightly. These pulsations cause the sun's brightness to fluctuate, making the light that bathes the solar system grow stronger and weaker with each cycle. It is as though the dying star has developed a slow, deep heartbeat in the darkness of space. For observers far away in the galaxy, our sun would now be seen as a variable star. Its light no longer shines with steady intensity, but waxes and wanes over regular periods. What was once a constant beacon now flickers gently, a star with a measurable pulse. Any distant astronomers would see the sun's brightness rise and fall like the breathing of a slumbering giant. During the sun's high seasons, when it swells and brightens, it sheds mass at prodigious rates. The outer layers, already loosely bound, are hurled outward in great streams and clouds of gas. A dense stellar wind carries off elements forged within the sun: hydrogen, helium, carbon, and more, sweeping them into the solar system. With each such active phase, the sun flings material into space, forming expanding shells of gas that drift off into the darkness. In one particularly violent cycle, the sun swells larger and brighter than ever, then abruptly contracts. This sudden lurch forces a huge bubble of plasma to detach from the sun's outer layers. That bubble of stellar material surges outward into space, expanding into a great billowing shell. The sun has effectively shed another piece of itself, flinging it off to join the growing nebula of gas around it. In the quieter, low seasons that follow, the sun contracts and dims slightly. The giant star seems to settle for a time, as if catching its breath, and its furious winds momentarily ease. Yet even in these calmer intervals, the sun remains immense and luminous, still far brighter than it was in its youth. These alternating phases of turmoil and calm define the sun's final chapter, a rhythmic end-of-life cycle playing out on a cosmic stage. In these cycles, the sun also expels not only gas, but dust. As the ejected material expands and cools, fine grains condense, forming clouds of cosmic dust around the star. At times, these dusty veils obscure part of the sun's light, causing it to flicker and dim even further from an observer's perspective. The sun's very colour may subtly change when shrouded by its own dust, adding another layer of variability to its final years. With each pulsation, the sun's cast-off layers form expanding shells around it. Ghostly halos of gas and dust drift outward, marking the history of the star's final breaths. The solar system is gradually filling with this tenuous nebula of stellar debris, a glowing veil surrounding the dying star. These expanding shells are the preludes to the sun's final transformation, the quiet heralds of the collapse to come. After the long red giant phase, a new drama unfolds deep within the sun's core. The core, packed densely with helium ash, has been growing ever hotter and more pressured. At last, it reaches a critical ignition point. The helium ignites in a sudden, runaway flash. In an instant, a tremendous burst of energy surges through the core as helium begins fusing into carbon. This helium flash is the sun's final, desperate bid for balance, a brief revival before the end. For a short time, perhaps around 100 million years, after the helium flash, the sun finds a new equilibrium. The core expands and cools slightly, causing the sun to contract from its former colossal size. It settles into a calmer phase, burning helium steadily in its center. The giant star's fury momentarily abates. The sun shrinks a bit and stabilizes once again. But this peaceful interlude cannot last forever. All too soon, the sun exhausts the helium fuel in its core as well. The core's fire fades once again, and gravity presses inward relentlessly. This time, no new source of fusion ignites. The core is now a ball of carbon and oxygen that the sun is too light to fuse. Without any nuclear pressure left to support it, the core begins to collapse one final time. As the core contracts for the last time, the sun enters its final throes. The outer layers respond by billowing outward again, creating an even larger, but more tenuous giant star. the sun reaches a second extreme of size, swelling and pulsating unpredictably in this final giant phase. In this last gasp, the sun sheds its outer layers at a tremendous rate, casting off its remaining mass and preparing to expose its naked core. Layer by layer, like the peeling of an onion, the sun's outer envelope is expelled, driven away by pulsations and fierce radiation. These cast-off layers drift into space, forming an immense expanding shell around the star. The dying sun is now shrouded in a glowing cloud of its own material, a nascent planetary nebula surrounding its core. At the center, the core continues to contract and heat, becoming a small, intensely hot point of light, the emerging white dwarf. The once mighty sun is about to collapse into an object no larger than Earth. Now the sun's final transformation is at hand. There will be no supernova firestorm. Our sun is not massive enough for such a violent end. Instead, it will die with a quiet dignity, a gentle fading that is the fate of countless stars like ours. The layers it has shed will soon blaze as a magnificent planetary nebula, shining in multicolored hues like a cosmic blossom in the darkness. At the center, the core contracts into a white dwarf, a tiny, searing stellar ember. This collapsed core will be no larger than Earth, yet will contain nearly half of the sun's mass, packed so densely that a mere spoonful of its matter would outweigh a mountain. The once life-giving sun will endure only as a dim white ember, wrapped in the ghostly glow of its shed layers. The day of its collapse is imminent. All that remains is for our star to take this final step and quietly fade into the cosmic night. The sun's long story will soon end, in silence and starlight. The beautiful nebula it leaves behind will be only a transient glory, dispersing into the interstellar void in time. Now, deep inside the aging sun, a new fire is kindled. The core, once filled with inert helium ash, reaches an extreme tipping point. In a flash of fury, hidden beneath the sun's glowing surface, helium atoms begin to fuse together. 3 helium nuclei slam into each other, forging a new atom of carbon in a moment of sudden brilliance. For an instant, the heart of the sun blazes as never before. A tremendous wave of energy ripples through the core, as if the star is experiencing a silent, internal explosion. This is a second dawn inside the sun, a helium flash igniting all at once. Yet, from the outside, there is little hint of this turmoil, for the energy is swallowed up by the sun's enormous bulk. Within mere minutes, a significant portion of the sun's helium is transformed. The flash produces as much energy as billions of years of ordinary sunshine, but nearly all of it is spent reshaping the star's interior. The core, once crushed and stagnant, expands and releases itself from its degenerate grip. It's as though the sun's heart heaves a sigh of relief, having finally found a new way to burn. In the aftermath of this internal eruption, the sun's behavior changes dramatically. The sudden helium burning stabilizes the core, and the star finds a brief new equilibrium. The gigantic bloated red giant begins to contract, its outer layers responding to the altered core conditions. Over the next thousands of years, a mere heartbeat to a star, the sun shrinks from its colossal size, relinquishing much of the swollen glory it attained as a red giant. The outward change in the sun is dramatic, though it unfolds over a few millennia. The sun's bloated envelope contracts remarkably. At its red giant peak, the sun had swollen so large that it engulfed the inner solar system. Now it shrinks to a fraction of that size. Where it once spanned the orbit of Mercury or beyond, it pulls back to perhaps 10 times its original radius, enormous by our current sun's standards, but a shadow of its former giant self. The star that filled our sky now would appear smaller and more concentrated again, its surface gravity tightened and its outer layers closer into the core. With this contraction, the sun's luminosity also drops to far less extravagant levels. During its red giant climax, the sun shone thousands of times brighter than in its youth. After the helium flash and contraction, it might glow only a few dozen times brighter than today's sun. This is still a luminous beacon, but nothing like the overwhelming brilliance of its red giant days. For any surviving worlds nearby, the difference would be stark. The blistering red furnace in the sky replaced by a more modest, warmer-coloured star. The sun is now steadier and more compact, emitting a gentler radiance than the fevered luminosity of its prior phase. The sun settles into a quieter phase under the gentle glow of helium fusion. Deep in its core, helium is steadily fusing into carbon and a bit of oxygen, providing a new source of energy. The star's surface cools slightly, and its colour shifts from the intense red of its previous giant phase to a softer, honeyed hue. The once ferocious luminosity of the red giant diminishes. The sun is now bright, but only a fraction as blinding as it was at its crimson peak. For a time, peace returns to our aging star. The helium in the core burns in a controlled fire, no longer wild and explosive, but calm and sustaining. The star's radius has contracted to something more modest, perhaps only 10 times its original size. In this period of respite, the sun is more stable again, holding itself together with the newfound balance that helium fusion provides. This phase, however, is a fleeting triumph. Compared to the billions of years spent burning hydrogen, the helium supply is scant and will not last long. For roughly only 100 million years, a fleeting episode compared to the sun's 10 billion year main sequence life, the sun can continue this gentle helium burning. It is a short-lived second life, a golden autumn after the long summer of the main sequence. The sun shines contentedly on borrowed time, unaware of how quickly this last fuel will be exhausted. In these final stages of burning helium, the core quietly accumulates the fruits of this new fusion. Carbon and oxygen, elements that once did not exist in the sun's center, are now steadily building up at its heart. These heavy elements are the ashes of helium's fire, and they are the seeds of future worlds. Carbon that may one day form diamonds in distant planets. Oxygen that might one day be breathed by living creatures elsewhere. For now, they remain locked in the sun's hot core, signposts of the star's irreversible evolution. Though the sun appears steady again, a subtle tension is growing within. Helium fusion yields less energy per atom than hydrogen fusion did, and the sun must work harder now to shine. The balance it has achieved is delicate, and the clock is ticking on its final reserves. The star's core is slowly becoming a dense sphere of carbon and oxygen, and as helium is consumed, that core grows in mass and pressure, inching towards another crisis. Yet outwardly, for now, the sun glows in serene dignity, its last great fuel burning steadily, a quiet victory over the darkness creeping in. Eventually, even the sun's supply of helium dwindles toward its end. The gentle stability the star enjoyed cannot last forever. When the helium fuel in the core is finally spent, the balance inside the sun shifts once more. Gravity begins to tighten its grip on the inert core of carbon and oxygen, squeezing it further now that no new fusion energy pushes back. As the core contracts, something dramatic happens in the surrounding layers. Just above the shrinking core, a shell of helium ignites into fusion, even as a shell of hydrogen continues to burn further out. The sun's energy now comes from these thin shells wrapped around the dense core, and this arrangement is inherently unstable. The helium shell does not burn smoothly. It flares up in sudden bursts. Periodically, helium fuses in a runaway surge, a thermal pulse, flooding the star with a brief blast of energy from within. Each time one of these pulses erupts, the sun responds like a giant bellows. A wave of heat races outward from the core, causing the outer layers to expand even more. The star swells rapidly, its radius pushing outward to extreme lengths. Then, after the pulse passes, the star contracts again slightly and quiets, only to await the next outburst. These oscillations grow more intense as the sun struggles through its final acts of fusion. In these convulsive throes, the sun's appearance becomes wildly variable. It is as if the star is breathing, each breath a colossal heave that makes it brighten and dim in cycles of tens of thousands of years. During a pulse, the sun can become thousands of times more luminous than in its former peaceful days. Its surface cools to a deep red glow as it expands, then warms slightly as it contracts, flickering in brightness over millennia. If some distant civilization were watching, they would see the sun's light wax and wane on geological timescales, a star flickering in its death throes. With each mighty pulse, the sun is no longer able to hold on to its outer layers. The bursts of energy shove the sun's gaseous envelope outward, throwing vast amounts of stellar material into space. The star begins to shed its skin. Great clouds of hydrogen and helium, laced with heavier elements like carbon dredged up from the deep core, are cast off. These layers drift away from the star, forming expanding shells of gas that carry the sun's essence into the surrounding cosmic night. The scale of these ejections is almost unimaginable. In a single outflow, the sun can expel an amount of mass equal to several Earths or more into the void. Dust condenses in the cooling exhalations, creating sooty veils that shroud the star. The sun becomes cloaked in its own cast-off matter, surrounded by concentric ghosts of itself, shells of gas and dust that were once part of the sun's own body. To distant eyes, the sun would now be a dim, reddened star, its light veiled by the dust of its own making. Much of its brilliance would only be apparent in infrared wavelengths, as the cool dust clouds absorb the visible light and re-emit a gentle heat glow. Pulse by pulse, the sun is losing its substance. Over a few million years of this turbulent phase, a significant fraction of the sun's mass simply blows away. Stellar winds, driven by the intense light and the pulsations, carry off material at a staggering rate. The star that once held its family of planets with a firm gravitational grip is now literally evaporating. Its hold on its outer layers weakens with each passing century, allowing more and more gas to escape into interstellar space. As the sun continues to throw off its outer layers, it grows lighter and more fragile. No longer is it the robust main sequence star of ages past. It has become a bloated, tenuous giant that can barely contain itself. The core at the center grows ever denser and hotter as material rains down onto it between pulses, only to trigger yet another flash of helium burning that again blasts material outward. This stop-and-start rhythm is the death rattle of the sun's fusion life. Within the expanding shells around the star, new chemistry is taking place. Heavy elements forged in the sun's late life, carbon and oxygen from the helium burning, even traces of exotic metals from deep within, are carried outward by the stellar wind. In the cooling layers of gas, some of these elements begin to form tiny solid particles. Sooty carbon dust and silicate grains condense like ashes from a fading fire. These microscopic dust motes will eventually become part of the raw material for future worlds, a gift from the dying sun to the galaxy. Each pulse pushes the outer boundary of the sun's atmosphere farther into space. The sun, which once measured nearly 1,000,000 miles across, has now bloated to truly enormous proportions during its pulses. At its largest, it may swell to span over an entire astronomical unit, briefly grazing the space where Earth once circled. The giants Jupiter and Saturn now bask in the red glow of a star that engulfs much of the inner solar system. And even as the sun expands, its outermost layers slip away, so that space itself seems to flow outward from the star. The instability grows as the sun nears the end of its ability to generate energy. Each new pulse is slightly less energetic than the last, as the fuel in the helium shell is gradually used up. Yet each pulse manages to expel more of the sun's remaining outer layers. The once mighty star is being pared down, layer by layer, to its core. Surrounding the sun now are multiple concentric rings and shells of expelled gas, moving outward steadily, like ripples on a cosmic pond after a stone has been tossed in. And so the sun ascends this final peak of instability. It shines as a variable, flickering beacon, its light sometimes dimmed by the dust of its own making. The star's last acts of fusion are anything but quiet. Yet in the vastness of space, this violence unfolds in slow motion and silence. Over those final few million years, dozens of great pulses come and go, until at last they cease entirely. All that will remain is what the sun has cast off, and the hot heart lurking at its centre. The stage is now set for the sun's next transformation, one that will turn those drifting layers into a spectacle of haunting beauty. Far in the outer reaches of the solar system, the transformations of the sun are witnessed in eerie silence. On Neptune's cold moons and in the Kuiper belt beyond, the sky has changed profoundly. Once, not long ago, a bloated red giant sun loomed in their heavens, turning the distant night to a dim crimson day. For a time, these icy worlds felt the touch of warmth. Frozen gases melted, thin atmospheres stirred, and alien dawns broke where perpetual twilight once ruled. It was a brief summer for the outer solar system, a strange and sudden thaw after eons of frigid darkness. During that interlude, worlds that had always been frozen found themselves transformed. The methane ices on Pluto and Triton vaporized into hazy atmospheres. Saturn's moon Titan, ordinarily cloaked in frigid gloom, might have warmed enough for its liquid hydrocarbon lakes to expand and misty rain to fall under a dim red sun. Even the icy surface of Europa, Jupiter's frozen ocean moon, could have felt a shallow thaw at its surface. These distant landscapes experienced a surreal twilight glow and gentle warmth that they had never known before. But like a winter rose, opening only briefly in an unexpected thaw, these changes would not last. Now that time has passed. The sun has shed its swollen red giant form and collapsed into a much smaller, hotter core. From Neptune's vantage, the sun is no longer a vast ruby orb painting half the sky. Instead, it has become a tiny, piercing point of brilliant, white-blue light. Though incredibly hot, this new sun is far less luminous than the giant it was. Its light reaches Neptune as a pale echo of its former glory. The fleeting warmth that bathed these distant worlds is gone, and an eternal winter has descended once more. In Neptune's sky, however, there is a new ghostly apparition. The remnants of the sun's outer layers, now forming a glowing nebula, stretch across the darkness. To an observer on Neptune, the heavens are graced by a faint, shimmering ring of light encircling the tiny star at the center. It is as if an enormous, delicate veil has been hung in the cosmos. In Neptune's perpetual night, that ghostly ring might even cast a faint tint on the icy landscapes. A dim aurora of red and green glowing on distant horizons, the final twilight of the sun's long life. The nebula's glow is subtle out here, a tenuous band of colour that arches across the black sky. Yet, on the very edge of perception, it is unmistakably there, the final aurora of a dying sun, writ large across space. Neptune's own clouds and atmosphere reflect some of this otherworldly light in unusual ways. The planet, a giant ball of methane blue, now drifts under a sky where the sun is a brilliant spark and the nebula a dim halo. As the planetary nebula expands, parts of it may even envelop Neptune's orbit, briefly surrounding the planet in a faint cosmic mist. Imagine the horizon on a moon of Neptune, a dark landscape illuminated by the soft glow of nebula light. No human eye is there to see it, but it is a sight of quiet grandeur. The sun's discarded glory subtly lighting the far frontier of its realm. As the sun's mass has waned, so too has its grip on its far-flung children. With nearly half its mass lost to space, the sun's gravity has weakened. Neptune and the other surviving planets have drifted into slightly more distant orbits, released a bit from the tight leash that once bound them. The outer planets continue to circle loyally, but their paths have expanded. Further out, in the comet fields of the Oort cloud, the change is even more profound. Countless frozen wanderers at the solar system's edge feel the sun's embrace slacken. Some of these distant icy bodies, barely held for billions of years, now slip free of their orbits and begin to float away into interstellar space, emancipated by the sun's great shedding. For the outer worlds that remain, the environment has shifted to an even deeper chill. Pluto and its brethren, which may have briefly grown hazy atmospheres under the red giant's warmth, have seen those vapours refreeze onto their surfaces. Any transient lakes or flows of liquid on faraway moons have solidified again into stillness. The grand experiment of warmth in the Kuiper belt is over. These distant realms return to their quiet, frozen states, illuminated faintly by the distant point of a white dwarf sun and the diffuse glow of the nebula around it. Jupiter and Saturn, once modestly warmed by the giant sun, are now plunged back into deep cold. Their cloud belts and rings lie under a feeble starlight, casting barely a twilight glow. Neptune itself, a gas giant, continues its lonely journey around the diminished sun. The sunlight now arriving is meagre, barely enough to cast a shadow, though the star itself glitters intensely if one were to look directly at it. The nebula's luminescence gives Neptune a strange sky glow at times, a soft radiance that is unlike the direct sunlight it knew. This light is not enough to warm anything. It is purely a ghostly illumination, a reminder of the sun's final act. In this fading sky, the planets bid their silent farewells. No more will there be the bright golden daylight that the sun once provided in its youth. No more the ruddy half-light of the giant sun that swelled in its old age. Now there is only the stark, tiny star and its fading nebula shroud. Yet even in this diminished state, the sun's influence lingers. It still holds its planets in thrall, still provides a glimmer of light to mark day from night. For any observer on these worlds, the transformation of the sun would be at once awe-inspiring and melancholy. A powerful star reduced to an ember, surrounded by the ghost of its former self. As Neptune and its fellow outer planets continue their orbits through this transformed solar system, they carry with them the memories of what once was. The great red sunsets of the giant sun are gone, replaced by a dim, perpetual dusk. The sky above is a tapestry of faint nebular glow and distant stars, with a single piercing point where the sun now lives. It is a scene of cosmic solitude. In the far distance, the nebula slowly disperses, and with each passing millennium, the glow overhead weakens. The outer worlds will watch the final light of their parent star fade gradually, keeping vigil in the cold. Even as the darkness deepens, something of the sun remains with them. The atoms that once warmed their skies are now drifting outward, some passing by these planets on their way to the great beyond. In every grain of dust that sweeps past Neptune, a particle of carbon, a molecule of water, there is a fragment of the sun's body making its journey outward. The outer worlds are saying their farewells not with words, but by witnessing the gentle departure of the sun's essence. In the quiet of the Kuiper belt and the Oort cloud, the story of the sun's final chapter is written across the heavens. A fading sky, a lingering glow, and the enduring presence of planets that continue to circle a much-changed star. In the core of the sun, a silence falls that has never been before. After the tumult of the final pulses, there comes a moment when the nuclear fires flicker and die out completely. The last atoms of helium in the shell have fused and been spent. No new fuel remains that the sun can ignite. This is the sun's last breath of fusion, a quiet and unceremonious end to an era that lasted billions of years. For eons, the sun's identity was defined by the fires in its heart, from the gentle hydrogen flames of youth to the fierce helium burning of old age. Fusion was the engine of its existence. Now that engine has stalled. Deep inside what remains of the sun, temperatures and pressures fall just short of what would be required to ignite the next element. Carbon and oxygen, the ash of helium's brief triumph, are plentiful in the core. Yet the sun is not massive enough to push these ashes into a new fire. They will remain forever as inert cinders, never to blaze as fuel. The cessation of fusion is a turning point, beyond which the sun can no longer call itself a true star in the traditional sense. It has expended all the nuclear fuel it was capable of burning. The raging furnace that once illuminated the solar system has gone out, leaving only a lingering afterglow of thermal energy. For a brief period still, the core radiates intense heat, but this is not generated by new fusion, only the gradual release of energy stored in the past. It is as though an enormous furnace has been shut down. The embers are hot, but no new fire feeds them. In that final moment of fusion, an almost imperceptible change passes through the sun's core. A kind of settling occurs as the furious cycles of atomic alchemy come to rest. The core, now a sphere of degenerate matter, simply holds its heat and glows, no longer transforming one element into another. If one could stand at the core, a fantastical notion, given its density and heat, one might imagine an immense stillness, a quiet end to the incredible atomic dance that once powered the star. Without fusion pushing outward from the center, the sun's remaining structure adjusts to a new reality. The core is supported entirely by quantum pressures of its dense matter, resisting further collapse, not by burning, but by the strange principles of electron degeneracy. Above the core, what is left of the sun's inner layers quickly cools and drifts away or settles onto the core itself. The sun has effectively lost the battle to sustain itself. The star's outer envelope, already mostly cast off, no longer receives any energy from below to hold it aloft. What little remains of the sun's atmosphere either escapes into space or falls back down, blanketing the core in a final thin shell of gas. The end of fusion is not marked by any explosion or grand event visible from afar. That drama has already played out in the pulses and ejections. Instead, it is like a candle flame quietly going out when the wick is gone. One moment there is a flicker of burning helium, the next, darkness in the core. The sun's luminous output does not immediately vanish. The core is still extremely hot, but from this point forward it will only fade, never again to flare brighter from nuclear fire. This profound finality might be imagined in human terms as the last heartbeat of a long-lived creature. After it, a calm sets in, an irreversible stillness. The mighty sun, which once roared with the continuous fusion of countless atoms, has entered a new stage of quiet. Its life as a star, a churning, fusing, radiating being, is effectively over. Had the sun been much more massive, its ending might have been far more dramatic. Perhaps it could have concluded in a thunderous supernova explosion, or ignited heavier elements in one last surge of fury. But for a star of one solar mass, nature charts a quieter course. The sun is not destined for any final cataclysm or further fusion. It will simply fade away in stages, having reached the limit of what it can burn. With fusion's end, the sun's future is one of gradual dimming. No new energy will replenish the heat that radiates away into space. Every photon the core emits now is one it cannot replace. Slowly, but inexorably, the sun begins to cool. The brilliance at its center, while still intense, has peaked and will only wane over the coming eons. This is the twilight of the sun's life, a glow that comes not from burning fuel, but from the fading memory of yesterday's fire. Even in this quietus, there is a certain dignity to the sun's final transition. It does not collapse in a brilliant supernova or tear itself apart. Instead, it gently transforms into a stable, if inert, form. Suns of far greater mass meet their end in spectacular explosions. But our sun's farewell is comparatively peaceful. The last breath of fusion is a soft sigh, releasing the star from the cycle of burning and into a calm repose. This calm will last for an unimaginable future, as the sun's core slowly cools across timescales that dwarf its active lifespan. In cosmic terms, the extinguishing of the sun's fusion marks the end of an era, but not the end of its story. A new chapter is beginning, one characterized by endurance and slow change. With its nuclear fires out, the sun becomes something else entirely, a pale star of the ashes, shining weakly yet persistently. This new sun will not create light through fusion, but will still glow from its residual heat, a cinder of what it once was. The last breath of fusion is both an ending and a subtle beginning, the beginning of the sun's life as a ghost of a star, carrying on without a flame. Freed from the star that once held them, the sun's cast-off layers continue their journey outward. What was once tightly bound to the sun, its very substance, is now unbound, drifting as part of the Great Galactic Sea. The planetary nebula, in all its glowing glory, is the visible sign of this dispersal. Over time, these shells of gas will stretch thinner and wider, blending gradually into the interstellar medium. The Sun's material is no longer confined to a single star or a single solar system. It has been returned to the galaxy at large. As the years pass into millennia, the nebula's edges diffuse into the surrounding space. The distinct bubble of light becomes ever more tenuous, until one day it will be indistinguishable from the general gas and dust between the stars. But this does not mark the end of the Sun's presence. In fact, it marks a new beginning. Every atom that drifts away from the fading nebula carries with it the legacy of the Sun. These atoms join the vast clouds of interstellar matter, the raw material from which new stars and planets will one day form. The elements forged in the Sun's final stages are among those now scattered to the cosmos. Carbon and oxygen, those products of helium fusion in the core, are blown into space to enrich the galaxy. Along with them go the lighter gases, hydrogen and helium, that once formed the Sun's outer layers. Tiny grains of dust, condensates from the cooling winds of the dying star, also float away like dandelion seeds cast into a breeze. Within those grains are more complex compounds, perhaps silicon minerals or carbon soot, all formed in the star's last breaths. This material drifts outward, a fine mist of star stuff expanding through the Milky Way. At this moment, the Sun is unbound, no longer a single, cohesive sphere, but a widening cloud of memory. If one were to look at the Milky Way from afar, the contribution of the Sun's shed layers would be imperceptible, just a tiny addition to the galactic tapestry. Yet on the microscopic level, the Sun's identity persists in each particle. A lone carbon atom, once nestled in the heart of our star, may travel for millions of years through space. It could become part of a cold molecular cloud wandering the galaxy, tumbling end over end through the void, until at some distant point it is drawn into a new sun's birth. In a sense, the Sun's death enables new life. The substance that was too bound up in one star to participate in anything else is now free to join new cosmic endeavors. Perhaps thousands of light years away and millions of years hence, some of the Sun's atoms will find themselves clumping into a dense region of a nebula, where gravity begins to pull matter into a new star. When that star ignites, a piece of our Sun will burn bright once more, contributing its essence to a new generation of starlight. Not all of the Sun's cast-off matter will form new stars. Some may become part of planets, moons, or even living organisms on those future worlds. The carbon that came from the Sun's core might be integrated into the molecules of a distant alien plant. The oxygen might one day be breathed by creatures who never knew the star it came from. In these ways, the Sun's unbound layers ensure that the story of our star continues, interwoven with the stories of stars and worlds yet unborn. For now, however, the immediate journey of these layers is a gentle dispersal. The expansion of the nebula carries them outward, slowing as it cools, mixing with any stray interstellar gas in its path. Some portions of the gas will be sculpted into complex shapes by the remaining stellar breezes and by motions through the galactic environment. Over tens of thousands of years, the Sun's once bright nebula will fade into a ghostly remnant, then effectively vanish as a recognizable object. Its atoms will have spread so thin that they blend seamlessly with the atoms that have come from countless other dead stars over billions of years. It is humbling to realize that this unbinding is the fate of most stars. To give their substance back to the galaxy, the sun is now part of that grand circulation of matter. Long ago, before the sun was born, other stars lived and died, and their expelled matter gathered to form the cloud that became the sun and its planets. Now the sun contributes in return, paying it forward by seeding space with the materials that once made up its shining form. In the stillness of space, each particle drifts in silence, carrying a story of solar winds and giant flares, of the warmth that once bathed Earth, of the nuclear alchemy deep in a star's core. Those stories disperse, but they are not lost. They will recombine with other tales of other stars, and in that recombination, something new will eventually form. New lights will spark in the galaxy, nourished in part by what the sun has given. The unbinding of the sun is a quiet liberation. Gravity's chains, which for so long kept every atom orbiting the star's core, have been unlocked. The sun's children, its atoms, are free to wander. Some will travel relatively nearby, perhaps to be swept up by the gravity of neighboring stars. Some might eventually be captured by those stars forming planetary systems. Other particles will journey for millions of years, crossing spiral arms, maybe never settling until the end of time. In whichever case, the sun's presence is now diffused throughout the Milky Way like an echo. As we reflect on this phase, we can imagine the sun, once a proud, solitary beacon, now surrendering itself to something larger. The boundaries between the sun and the rest of the galaxy have dissolved. There is no longer a clearly defined sun in terms of material. Only the core remains distinct. The rest is part of the galactic whole. In this way, a star's end is a form of reunification with the cosmos, a giving back of everything it once held tight. This unbound sun, spread out across space, ensures that in the tapestry of the galaxy, the thread of our star will be woven into countless new patterns in ages to come. In the silent darkness of space, the sun's former glory lives on as a glowing cloud. This planetary nebula is more than just hot gas. It is a cloud of memory, a luminous record of the star that created it. Gases that once resided deep within the sun now shine on their own, suspended in the cosmic night. They form a spectacular apparition, a reminder that even after death, something of the star remains, lighting up the void in a gentle, final display. This nebula is like a portrait painted by the sun in its last moments, each colour and shape telling part of its story. The diffuse hydrogen that dominated the sun's outer layers now emits a faint crimson hue along the nebula's edges. Helium, the ash of billions of years of fusion, glows in soft peach tones closer to the core. Woven through these are the fingerprints of oxygen and nitrogen from the dying star's interior, adding subtle greens and blues to the spectral canvas. These gases glowing in the dark are the sun's farewell message, radiating out for anyone or anything that might be watching across the light years. In the vast cosmic emptiness, the nebula's glow might seem fragile. It is a tenuous sheen of light against an ocean of black, but it holds its own, a delicate lantern hanging in the abyss. Within it, every filament and wave of gas corresponds to an event in the sun's final chapters. A pulse that expelled this layer, a breeze that shaped that curve, a molecule that condensed in the chill of space. The nebula is rich with the silent echoes of those events. It stands as a three-dimensional memory map of the sun's dying breath. If one could drift through the center of this nebula, the view would be otherworldly. The sky would be aglow on all sides with faint color. You would be floating through the ghost of a star, surrounded by the atoms that once made up its shining form. Here and there, pockets of denser gas form knots or clumps, like recollections gathering strength. Elsewhere, thin, almost transparent regions barely hint at the star stuff, spread so finely that only the most sensitive instruments could detect it. Yet all of it together forms a coherent presence, a cloud that in its entirety reflects the sun's existence. A cloud of memory is an apt description, for like a memory, this nebula is fleeting. It hangs visibly in the darkness only for a short while on cosmic timescales. As long as the central core remains fiercely hot, the gases continue to fluoresce, illuminated by ultraviolet rays. The nebula's glow depends on the last vestige of the sun's energy. But as that energy diminishes with the cooling of the core, the nebula will gradually lose its luminescence. The memory will begin to fade. The once bright edges will grow dim, and the colors will blanch back into the blackness of space. Yet, while it shines, the nebula ensures the sun is not forgotten. And it is not alone. Throughout the galaxy, countless such clouds of memory glimmer where other stars have died. The night sky of Earth has revealed examples of these cosmic memorials. The Ring Nebula, the Dumbbell Nebula, the Cat's Eye Nebula. Each is a glowing shell of gas, marking a star's life that came to an end. Our sun's nebula will one day take its place among these cosmic jewels, a small but meaningful addition to the galaxy's collection of stellar remembrances. Across the galaxy, anyone who could see this faint patch of light would know that a star has passed through this place and left a testimony. It's a cosmic epitaph written in glowing gas. In that radiance, one can read the fact that here a star lived, grew old, and died, and in its dying cast its essence outward. Long after any planets or life that once basked in that star's warmth have gone, this luminous cloud remains to speak of the star's life. There is a haunting beauty in such a ghostly apparition. The nebula's light is steady and calm in human terms, changing only slowly over centuries. It doesn't flicker like a flame or roar like the sun did in its prime. Instead, it glows with a peaceful certainty, as if embracing the quiet after the storm. In the darkness, it has no competition. The stars' planets are dark cinders now, and the distant stars of the galaxy are far away. The nebula floats alone, a solitary memorial candle left burning in a great dark hall. The gases themselves, once heated to incandescence, gradually expand and cool. During the height of the nebula's brightness, collisions of energetic light with atoms cause those atoms to emit photons, creating the visible shimmer. One by one, as the core cools and the expansion continues, those collisions become less frequent. The nebula's own growth works to extinguish its light. As it stretches, it thins. As it thins, its brightness wanes. The cloud of memory is delicate, spread too thin. It can no longer hold on to the light that gave it life. In this moment in time, however, the cloud still thrives as a beacon of the past. It is not merely a passive remembrance. It actively shines, radiating away the energy that the sun imparted to it. Every ray of light the nebula emits is a little piece of the sun's history being shared with the universe. Photons generated by the sun's core long ago now bounce off these gas atoms and journey outward, some escaping the nebula entirely to travel indefinitely through space. In a way, the nebula is broadcasting the sun's story, in code, through those photons that carry subtle signatures of the elements present and the processes that occurred. As we gaze upon this image of gases glowing in the dark, we understand that this is an intermediate between presence and absence. The sun is no longer a star as it was. It has died, and yet it has not entirely disappeared. The core remains, and around it, the luminous cloud drifts. It's as though the sun has become both mourner and memorial. The small core is the mourner, a lonely point of light, and the nebula is the memorial, a diffuse monument to all that the sun once was. Together, they persist for a time, holding the space where once a vibrant star lit the sky. This cloud of memory will continue to glow for some thousands of years, gradually dimming until night dominates once more. But even after it fades beyond visibility, the material it leaves behind will remain as a subtle enrichment of space. Perhaps no longer luminous, but still there, a lingering trace. And the sun's story will have been passed on through those materials, ensuring that nothing truly vanishes without a trace. For now, though, we still behold the noble sight of our star's memory, suspended as a glowing cloud against the infinite dark, a poignant and peaceful testament to the sun's final chapter. At the center of the expanding nebula lies the sun's transformed heart, now fully unveiled. What we see is the sun's core, alone and exposed to space, shining with a fierce but steady light. The star we once knew has become something entirely new, a white dwarf, a silent stellar ember. Gone are the raging nuclear fires and the bloated layers of glowing plasma. All that remains of the sun, as it once was, is this compact, extraordinarily dense sphere, quietly radiating away its heat. This white dwarf is diminutive in size, astonishingly so compared to the giant it once was. It is roughly similar in scale to the Earth in diameter, yet contains about half the mass of the original sun. In other words, we have the weight of half a star compressed into a volume only a fraction the size of Earth's orbit. The matter in this core is in an exotic state, electron degenerate, squeezed so tightly that a spoonful of its substance would outweigh a mountain. It's almost impossible to fathom. A single teaspoon of white dwarf material could be as heavy as an entire skyscraper. This is the sun's core laid bare, matter at the verge of what physics allows it to be. The core's surface gleams white hot, tens of thousands of degrees and more. Initially, it may exceed 100,000 degrees, emitting a brilliant blue-white light, rich in ultraviolet. To the eye, if one could approach it, it would appear as a point of searing brightness, tiny and intense, like a diamond catching the light. In fact, the analogy is fitting. The sun's core is composed largely of carbon and oxygen, and as it cools over the eons, it is expected to crystallize. One could poetically say that the sun will eventually become a cosmic diamond, a jewel in the darkness, albeit one that no one may ever see up close. Despite its extreme heat, this new stellar remnant is relatively faint in visible light compared to the sun we knew. Its small size means it has far less surface area from which to radiate. While it still shines, with perhaps a few % of the sun's original luminosity, the quality of its light is different, more piercing, bluer, and concentrated. Much of its energy pours out in ultraviolet rays, which is why it lights up the nebula around it so effectively. But to any distant onlooker, as the nebula fades away, this white dwarf will appear only as a faint star, gradually becoming dimmer as millennia turn into millions of years. Within the white dwarf, no sound of fusion rumbles anymore. The core is silent and still in terms of nuclear reactions. The pressure inside is supported by electron degeneracy, a quantum mechanical resistance to further compression, rather than by the explosive outward push of fusion. If the earlier sun's core was like a busy forge, hammering and burning, now it is more like a hot, solid ball quietly cooling off. The sun has become an inert, glowing cinder, extraordinarily hot and bright at first, but ultimately destined to fade. This transformation is one of the most profound in stellar evolution. From a main sequence star to a red giant, and now to a white dwarf. Each phase is dramatically different, and this final stellar remnant is perhaps the most unassuming in appearance. There are no flares or prominences here, no swirling storms on its surface, just a smooth sphere of dense matter radiating a steady glow. Its silence is not just literal, there are no more explosive reactions within, but metaphorical. It no longer has the volatile life of a star, only the quiet aftermath. The gravity at the white dwarf's surface is immense. Any residual thin atmosphere around it, mostly hydrogen or helium that wasn't lost, clings in a shallow envelope mere kilometers thick. If an object were to fall toward the white dwarf, it would slam into the surface at incredible speeds, accelerated by the intense gravity. But such events would be rare. With the surrounding nebula dispersing, there is little left to rain down onto the core. In this new state, the sun's heart will simply shine and cool, with perhaps occasional subtle pulses or flickers as it adjusts, for even white dwarfs can tremble slightly as they release heat. For the most part, however, this is a stable and enduring final form. It's worth reflecting on the journey to this point. The core we see now once powered the solar brilliance that sustained life on Earth. It fused hydrogen into helium for billions of years, then helium into carbon and oxygen as the star aged. Layer by layer, around it, the sun's structure evolved and then fell away. Now that core stands alone, composed of the very elements it created during its life. The sun has, in essence, forged the materials of its own tomb, a carbon-oxygen core that now serves as its final state. The sun has become something new, and yet something very old in cosmic terms. White dwarfs are often called degenerate stars, and indeed this stellar remnant is no longer a star in the usual sense of ongoing fusion. But it still carries the light of the sun, now locked in a much smaller, denser package. This white dwarf will persist for an astonishing length of time. Long after the nebula has vanished, long after the memory of the sun's former glory has scattered to the corners of the galaxy, the white dwarf will remain, slowly cooling over billions upon billions of years. In the far future, it will transition from white-hot to blue, to yellow, to red, and eventually to not visible at all, becoming a so-called black dwarf, a cold, dark sphere. That last phase is so distant that the universe itself may have changed in unforeseeable ways before it comes to pass. For now, what exists is a silent sentinel at the center of what used to be the sun's domain. The sun has become this new thing, small, incredibly dense, brilliantly hot, and surprisingly modest in its output. There is a serenity to it. After all the tumult, the nova-like flash of helium ignition, the throes of the red giant, the casting off of layers, we are left with a quiet, enduring core. This is the sun's new identity, a white dwarf star, the final shrine of all the solar fires that once were, shining softly in solitude. In the aftermath of the sun's demise, a final gift illuminates the darkness, the gentle radiance of the planetary nebula, a beauty born from death. It is a scene of quiet grandeur. The once turbulent star has left behind a vision of elegance, glowing rings and filaments that drift through the void, lit by the fading heartbeat of the star at their center. This lingering light is the sun's last encore, a final performance that transforms destruction into art. The nebula's colors and shapes are breathtaking to behold. Swirls of pale red and violet trace the outlines of gas that was cast off in sorrowful bursts, now dancing in slow motion. Iridescent sheens of green and blue from oxygen and other elements create a delicate tapestry against the black of space. It is as if the sun's soul has blossomed outward into a cosmic flower, each petal a translucent sheet of glowing gas expanding gracefully. In this spectacle, we find a profound truth of the universe. Even in death, there can be beauty and rebirth. For a star like the sun, this nebula is the crowning finale, a phase both ephemeral and glorious. Long after the searing heat of the core has subsided, the light in the nebula persists, softly fading. The nebula will shine for only a few tens of thousands of years, a mere blink by cosmic standards. And yet in that brief time, it will give the universe a radiant display. Many such displays have come before from other stars, and many will come after. But this one is ours, the swan song of our sun, casting a gentle glow over the ruins of its solar system. As we contemplate this scene, there is a bittersweet quality to it. The source of light, the sun's remaining core, is a reminder of finality, a small ghost of the star that was. And yet, around that ghost, the vibrant nebula proclaims that the end was not a simple extinguishing, but a transformation. The sun did not simply vanish. It became something that, for a time, makes the darkness around it richer and more alive. The cosmos is dimmer without the sun's full brilliance, true, but it is not dark all at once. The light lingers in the nebula, gradually dimming like the last embers of a once roaring fire, casting flickering shadows of memory on the cosmic walls. This luminous cloud will eventually spread out and dissipate, its beauty melting away into the wider galaxy. But before it does, it serves an essential purpose. It releases the sun's elements into space in a spectacular flourish. That flourish is as informative as it is beautiful. It tells any who look and understand that here, a star's life ended in a gentle dispersal, not in violence. Beauty born from death is not just a poetic turn of phrase. It's written in the physics of this moment. The death of the sun produced a nebula that will go on to seed new beauty elsewhere, even after its light fades. Already, the glowing gases are mixing into the galaxy, carrying the sun's legacy with them. In the eerie glow of the nebula, one can sense a feeling of closure and continuation at once. It is the closure of the sun's active life, but the continuation of its influence. The radiant cloud and the tiny white dwarf at its center stand together as a bridge between what was and what will be. The nebula's light will eventually wane, but the white dwarf will remain, carrying forward the memory of the sun in its silent, persistent glow. And long after the nebula's colors have dimmed beyond sight, the elements it shed will be forming new connections in the coldness of space. There is a calm to this final tableau that belies the turmoil that led to it. Drifting in space, the nebula makes no sound. Its motions are measured and graceful. The white dwarf at its centre no longer flares or rages, but shines steadily. The violence of the red giant phase, the convulsions of thermal pulses, all are over. What's left is serene, light and gas in delicate interplay. It reminds us that the universe often ends great acts not with a sudden silence, but with a gentle decrescendo, a soft fading out that leaves a memory imprinted in the darkness. As the light lingers in the nebula, we witness the paradox of an ending that creates something new. The sun's death has crafted a new celestial object, this planetary nebula, that never existed during its life. If an astronomer from another world were to stumble upon this glowing cloud, they might marvel at its structure and decipher its story, learning about the star that gave it birth. In that way, the sun's final act communicates across space and time, sharing its tale through beauty. And so, our sun's final flames unfold in quiet splendor. The destruction that could have been merely tragic has been transmuted into a scene of wonder. The cosmos is poorer by one shining star, but it is richer by the ethereal painting that star left behind, and by the promise of new beginnings written in its dust and light. The beauty born from the sun's death is not only a farewell, but also an inspiration, reminding us of the endless cycle of cosmic evolution, how dying stars pave the way for new stars, how even in endings there are seeds of creation. For now, the nebula remains visible, a slowly dimming lantern hanging in the emptiness, its glow a gentle reminder of the star that was. The white dwarf inside continues to shine, a pinprick of fierce light, ensuring the nebula stays lit from within. In time, both the lantern and its flame will diminish, yet the impact of this moment will echo forward. The atoms freed here will drift and someday find new homes, and the very existence of this nebula's brief radiance adds a note of beauty to the grand symphony of the galaxy. In this still moment, we linger with the light. We allow ourselves to absorb the serene beauty of the scene, a vision that is at once an ending and a promise. The sun's life, as we knew it, has ended, but the light it ignited will travel on. Even as this luminous nebula fades, it lights the way for a future built on the remnants and memories of what once was our star. In the sun's end, we find the echo of a pattern repeated countless times across the cosmos. Stars live, stars die, and from their remains, new stars and new worlds are born. Some massive stars end their lives in cosmic fireworks, supernovae that outshine galaxies, while much smaller stars simply fade away without fanfare. Our sun's final fate is a gentle middle path, a quiet scattering of its substance to seed the future. The final flames of our sun are thus not only a conclusion, but also a link in the great chain of cosmic evolution. As the nebula fades and the white dwarf quietly endures, the story of our star becomes one with the story of the galaxy. And in time, the cycle will continue. The darkness left behind will one day light up again in the birth of new stars, carrying forward the legacy of the sun in their shining cores.